right, hello. Well, thank you all for coming. Um, Appreciate the attendance here. So what I want to do is to get things started, I'm just going to do a quick introduction. So my name is Michael Rosas. I'm a VP and General Manager at Virtualware. We're a company that helps other companies adopt and scale XR technology. And so today what I want to do is I want to talk about harnessing the power of the industrial metaverse in the energy industry. So leveraging XR digital twins for real world impact. So to get started, what if I told you that the boundaries between the physical and digital worlds are dissolving? That factories, hospitals, classrooms, and even nuclear reactors are no longer confined by walls, distance, or even gravity. Sounds like science fiction, right? Well, it's not. This is what's called the industrial metaverse. And this is where digital twins, along with XR technologies, allow for human-in-the-loop interactions. So this is something interesting that we're seeing with a lot of companies nowadays, asking, how is it with all the digital things that are happening within my company, adopting especially digital twins, how is it that my workers have the ability to be able to interact with these digital data systems? And the way that we've been able to solve it is through XR technology, which allows you to go into these digital worlds that exist as if you're there in real life. So to get things started, what I'd like to do is maybe start asking yourself a little bit about what real world problems can I solve with XR? Because this is something that we had to ask ourselves when we were going through the process of how we contribute to this industry. And essentially what it was is that we saw that there was no one who was delivering to companies in a way that allowed them to scale this technology. Something that across their value chain could be something that they could deploy easily, creating content of digital twins, managing that content, and deploying it across their organization. So as you can see, oh shoot, sorry. I just realized. I got to be pressing this one too. So yeah, so there you go. There's an image of what the platform is like. As you can see, we allow you to create content, put it up to the platform, manage it, your users, your sessions, and then be able to deploy it in multiple different deployment methods, whether on a computer or in a multi-user immersive room. So essentially what we did is we said, we need to solve the problem of how companies can use this across their value chain. And so what you see here is that you start to create a digital twin once from the design phase. And on this platform, you could utilize it to design, prototype, create development, manufacture. So this one's big, especially right now. Create digital twins, assembly line, virtually plan, review, in optimized workflows before you even build. And then now you have a digital twin that allows you to, once it goes into production, you have the ability to train your operators in virtual settings. And I'm going to go into that a little bit more with actual real use cases. And then finally, promotion, which is actually a big one because it's the ability, especially when you have projects with, let's just say, large manufacturing facilities that haven't even been built yet. You could utilize the power of digital twins and XR technology to be able to visualize them to your clients and get the green light to move forward with a project. So let's talk a little bit more about some real world use cases within the energy industry in particular. So one of our clients is GE Vernova. GE Vernova has been in the nuclear space for many years, and at this moment in time, in regards to Canada, they're going to be building the first small modular reactor in Darlington, and this is a really big project with a lot of different partners involved, and this is something that we see as it's going to be groundbreaking in regards to, let's just say, the future of especially nuclear in Canada. So one of the challenges that they came to us with is improving operational safety and lowering the cost of training. What they had before was an actual physical replica of a nuclear reactor in San Jose, California, and they had to ship people from all over the world to be able to train in it. So you can imagine that's extremely costly. Also, you're taking people away from their work. And so what they did is they came to us and to see what kind of solution that we could come up with in regards to actually creating virtual digital twins of their nuclear reactors and creating all the processes exactly emulating how it is and being able to train their workers just in time, even before they even go out on into the nuclear plant. And so we went through the whole validation process, and that's something that they were able to validate. And then not only that, but they wanted to be able to scale it across their organization. So one of the interesting things is that in the small modular reactor that's going to be built, that's going to have this type of training. And this is going to be something that's going to help the future workforce of Canada in regards to them, before they even built it, start training on the actual reactors in a safe environment. So what is this doing? Oh, sorry. So there's a solution, and you can see here, this is one of a digital twin of one of the reactors. Obviously, being in it is much more interesting when you can actually sort of, but you can see here the pre-VR phase, again, the physical, and now they're scaling it over here. This is one of the rooms that they have where you could have multiple people working within these virtual environments, just as if they were in the real plant. Okay. Even interacting with machines, you can see here, you could be interacting with machines directly. So one of the next ones that we're doing is right now, actually, this recently launched, and this is Nexstar Energy. This is a new gigafactory that's being built in Windsor, Ontario. And one of the challenges that they have is training 400 new workers that are going to be working at this location. And so what they're doing is they're building digital twins of their factory facilities and then be able to actually train these workers and even qualify them. Not everybody's going to pass, and the ones that actually do pass then get to go to finish off in the actual plant. What they're doing is their costs are going down because they don't have to, it's allowing them to accelerate this, and it's allowing them to do this before it's even built. So this is something that, from my understanding, is a first within Canada. As you can see here, they have a traditional sort of training center, but we have a full virtual reality immersive room where you have multiple people working in here. So this is something that, again, that ability to be able to have digital twins, human in the loop, in a safe environment allows for companies to start to really use this and bring value to their operations. So you can see here, actually, this is one of the, they're doing a lot of campaigns for recruiting people, and it's been great. They've got all these job fairs, and they've had a lot of people applying. So this has also been really great for recruiting. And as you can see, we're working with different partners from Upskill Canada, Palette Skills. So this is a really interesting, and Invest Windsor Essex, who's the main partner there. So what I want to do is I wanted to give you some particular use cases, but I also just wanted to leave some 5 practical sort of step framework for real world impact. And so if you do consider utilizing this type of technology, what I would always encourage is identify the specific use cases, start small, find a particular problem where immersive tech can make a difference. For instance, could VR training enhance employee onboarding? Kind of like what we're doing with those projects. Build collaborative partnerships. You don't have to do it alone. Partner with tech providers, consultants, even competitors. Share knowledge and resources. This is something that we've been talking about too in regards to Canada. Different companies coming together with different resources and being able to actually put these types of programs together so that everybody could actually build and be more resilient. Invest in some skills development. Equip yourself and your team with some necessary skills. This might mean training in new software, understanding the basics of XR technologies to unlock future potential. And then I always encourage to build through iteration. Begin with pilot projects, learn from them, refine your approach, and then scale up, right? It's about continuous improvement. This is what we did with GE Vernova, and now they're at that scale phase where they're doing it across their organization worldwide, okay? So I'm just gonna leave you with one last thought here, and that is the immersive future, crafting our collective narrative. In the coming years, XR will intertwine with artificial intelligence, 5G, and beyond, creating richer, more responsive experiences. Digital twins may become as commonplace as physical assets, and the metaverse economy is anticipated to be worth $5 trillion. Will you be a passive observer or an active creator in this unfolding narrative? Just something to think about. So I want to thank you for having me present to you today. One of the things I always say is think big, start small, and scale fast. Feel free to reach out to me on LinkedIn if you'd like to learn more. Thank you very much for your time. Thank you.
Good morning, everyone. My name is Kais. I've been working with NanoPrecise for 2 years as digitalization expert. Today, I'm going to be presenting an energy-focused predictive maintenance solution. Before we start with our agenda, I would like just to highlight a common challenge that the manufacturing industry, the energy industry is facing, which is how can we cut our energy and carbon footprint. And one common equipment that it goes across multiple industries, which is the rotating equipment. So the electrical motor-driven equipment, they are responsible for around 65% of the total electricity globally, and around 20% of them, they are consuming more energy in a way or another. The point is, how can we cut our energy consumption, our electricity bills, while providing the value, which is kind of like shifting the management from the traditional way of only focusing on the operational side into more energy and the operational side. So if we look at the total cost life cycle of any equipment, purchasing the motor is responsible for around 1 to 2% of the total cost during the time. So if we look at the motor, around 97% of that is coming from the extra amount of energy that it's consuming. If we are look at the pump, which is kind of like not generating the energy itself, however, it's kind of like consuming the energy, what we see is around 45% of that energy is coming from there, as well as it's just because of these equipments are faulty. So if we look at the title of my presentation, it's about how the maintenance programs or the maintenance approaches have been evolving with time. So we start in the past with reactive maintenance, meaning that we only act upon the failure, which is kind of like one of the most examples about that is run to failure, which is all of the equipments are running. Once they are not running, they're kind of like getting into a failure, and then we act upon it. That keeps us with a high unplanned downtime. Another program with time that came, it's preventive maintenance. So preventive, it's more about preventing the failure before happening by having maybe like a time-based maintenance. That solves the problem a bit. However, it reached a point where the equipment are over-maintaining, meaning that it's kind of like highly costly. I'm going to be focusing now about the last two maintenance approaches, which is reliability maintenance and energy-centered predictive maintenance. Let's have a closer look on the differences between them. So when we are talking about reliability-centered maintenance, it's about identifying what's critical when it comes to the equipment, and then from the criticality, identify the faults in these critical equipment. Afterwards, we prioritize our maintenance activities depending on the fault or the severity of the faults, and then we act upon it. On the other hand, when we are looking at the energy center predictive maintenance, first thing, we identify the critical assets and the most energy consumption assets. The second step is basically draw or bridge the gap between the faulty assets and the amount of energy that they are consuming, making it easier for the users in order to do some prioritizations for what's critical, what's semi-critical, and where am I kind of like consuming the most amount of energy. So this one provided kind of like reduces the unplanned downtime while having kind of like our eye on the carbon emissions and on the energy consumption. Some numbers when it comes on, just to put some perspective into what does it mean to monitor 100 data points of motors, pumps, and so on. So what we see in the last couple of years with our customers, basically if we are monitoring around 100 sensors, we can save around 107 megaton from the carbon emissions. If we put it into a perspective, that means around charging 14.5 million smartphones. How does it work? So we follow 5 repetitive steps when it comes to the way that we reach the energy-focused predictive maintenance. First one, we collect the data. We look for any abnormality, which is kind of like more anomaly detection. Once we identify any abnormality, we identify the fault type. And then we can, by using AI and machine learning, we can predict the progression of the failure, and we present that in remaining useful life. And the fourth step, which is where we calculate the amount of energy that each one of these motors is consuming more. And the fifth step, which is while we are presenting the insights, and the maintenance teams, they can kind of like act upon it. So what you see in front of you is an idea not only about the status health or the health status, the remaining useful life. What you see also is the estimated weekly energy loss across each one of these components and the amount of CO2 emissions also across each one of them. The last thing that I have in my presentation is just two examples about some of our customers that we helped recently. So the first one is one of our food and beverage customers. They faced around 54% more energy. However, their production has increased only 5%, which doesn't make any sense. So when we dig deeper into the problem, what we saw, it was kind of like by monitoring all of the equipment, by addressing where the energy is consuming more, we could help them achieving 2x return on investment, as well as reducing the energy by 678,000. And again, if we put it into a perspective, it's around 1.2 million miles driving. This is the amount of carbon emissions that we could save by monitoring only 200 data points, or which is around 50 motor and pumps together. Another use case, which is a bit more maintenance oriented in the pharmaceutical industry. So we are monitoring around 6 sites, around 141 data points. Within 6 months, we saved around 136 hours from unplanned downtime and around 42,000 of the energy consumption across 6 different sites. A bit about our company. The headquarters is in Canada, in Edmonton. We have 5 offices. We have one in California, one in Berlin, Germany, and I'm part of the Europe team here. We just established another one in Dubai for the Middle East, and we have a major branch in India. We are more industry agnostic company. So we have around 121 active customers across 12 verticals. And this is just the type of customers or the verticals that we are targeting. We are not exhibiting in this hall. We're exhibiting in Hall 7 in the pavilion, also the Canadian pavilion. So feel free to reach out, just to swing by, say hi, and that's it. Thanks again, everyone.
Hello, check. Um, Good afternoon, everyone. This is Debjyoti Sen from Red Deer Polytechnic. I'll be talking about how we are enhancing our Energy Innovation Center in terms of integration of diversified energy system and reducing energy demand. So the presentation will go in twofold. One is how we are transitioning our energy system within our polytechnic, as well as how we are reducing our energy demand. Okay, here we go. So a little bit of history about Red Deer Polytechnic. Red Deer Polytechnic is located in Red Deer, Alberta. It's in between Edmonton and Calgary, two big cities. So we have a very strong applied research department at Red Deer Polytechnic, and I represent the Department of Manufacturing and Energy Innovation, currently leading the department as the director. So today we'll be talking about how we are solving some of the energy challenges within Red Deer Polytechnic environment. So I'll first answer why we are doing it, and then I will say how we are doing it and what we are achieving. So that's how the presentation will go. So why we are doing it? We are doing it to promote sustainability. We are doing it to promote training in alternative energy and energy transition. And at the end of the day, we want to save cost. Although sustainability, the word sounds very cool. Everyone uses that word in many different ways. But we are doing it for the genuine reason that we want to reduce our energy demand, and we want our energy to be more sustainable in terms of achieving some autonomy. As we know, due to global geopolitical situation, energy cost can change drastically. So we need to be self-sustaining, and to be self-sustaining, we have to identify what are the sources and how to integrate the sources. So presently, the whole world is going into electrification, and to do electrification, you need to combine different sources of energy. As we all know that renewable energy sometimes can not be reliable because the sun cannot stay forever, the wind is sporadic. So how do you get different sources of energy to interact with you to have a stable baseline? That's something we are looking into. We are also looking into energy storage, because you can have all the clean sources in the world, but if it's not reliable, then you need some sort of energy storage to have the stability in your performance. Now, the other side of the equation is people always focus on how can we be more green, how can we do the transition, but people don't look into how we can reduce the energy demand, because half of the effort, or I'll say more than 60% of the effort, is in reducing the energy demand, and you can achieve a lot just by reducing the demand, and then you can see like how much extra energy you need from your other sources. So we are working a lot on the energy demand side as well, and all of this comes to economics. So one of our goal is how we can reduce the energy footprint and the energy cost within our polytechnic and keep the operational budget low. So that's one of our goal. So a little bit of history. Our Energy Innovation Center is fairly new. So it was established in 2019, and we are targeting to be the first Canadian net zero post-secondary by 2031. So our research focus is very much industrial. So we look into diversified sources of energy, energy storage, and reduction of energy demand. We also focus on data-driven innovation, because we want to collect more data to answer some of the key questions. Like, for example, one of the key questions I get asked, does solar works in Alberta with so much snow in the winter and shorter days? So how do you answer a question like that if you don't have right amount of data? So we'll talk a little bit about what we have done in our data-driven journey to collect good quality data to make those decisions. What energy source is good? And obviously, we are a post-secondary institute with more than 13,000 learners. So we would like to promote education and awareness, not only to our students, to technicians, to industries, to our communities. And we do collaborate with our local industry, the utility provider. We promote small and medium-sized industry to come to us and work with us in our energy transition journey. So key focus area of our projects are data-driven innovation. So we have the largest data sharing alliance probably in Canada. So what we do is we collect data from different solar panels which are distributed in our campus as well as in our province. So we are expanding that nationally. So we have probably data going back to 2019. So we collected granular data. These are zillion lines of data that we have. So we do a lot of analytics on what are the causes of solar power generation and how to optimize the solar power along Alberta. So we have a concept called Living Lab. So we treat our campus like a small city where different companies can come and try their new technology. For example, if someone has a battery system, they can come and hook that battery system into our microgrid and see their performance before going all out to the consumers. So that de-risk many companies. We have our electrification projects which focuses on power analysis, simulation, and also we are setting up our microgrid as I have said. Then one of the recent research we are doing is in connected building, how we can optimize HVAC cost of the building, which is apparently 50 to 60% of the cost of running a building. And especially in a climate like Alberta, where there is huge temperature swing, most of the cost of your operation in a building goes into HVAC. So any percentage savings on that can amount you a lot of savings in your operational cost. So there are many companies who are interested in our connecting building concept. The way it's working is we are trying to reduce our operational cost and creating that as an example so that companies can come to us, plug in their devices and see how efficient that is. And if many companies become our partner, then we can benchmark how their systems works compared to their other partners or competitors. Now, this is what we have in terms of our infrastructure. To list the three key infrastructure, we have a capacity of 1.6 megawatt of solar power generation in our own campus, and we have 4,200 solar panels, so that makes us one of the largest solar panel array in all of Canada that we have in terms of rooftop solar panel. We have 1 megawatt of CHP, so combine these two, we can generate 60% of our energy demand today from renewable sources of energy. And we recently bought this battery. It's a 192 kilowatt of battery storage from Extro System. They are a local Alberta company based in Calgary. So we are testing their system in our grid to find out how their system performs, especially in cold environment. So we'll be furthering some of our research with Extro System in terms of how they can repurpose secondary batteries for electric vehicle use. So as we know, in 2030, a lot of the electric vehicles are becoming old. So their battery needs to be either recycled or it needs to be repurposed. So we are trying to find out how that will work. So there will be a research area that will start very soon on that. So we'll talk about our data sharing alliance. So this is one of the largest data sharing alliance right now in Alberta. So we collect data, we install something called e-gauges and sensors in our solar generation sites. We do data analysis, and within the data sharing alliance, there are partners with whom we benchmark and share data. So here are some examples of some of the interesting results that we'll show you. So we have data across Alberta coming from different partners. So one of the interesting data that I want to show you is this building. This is on our campus. So this particular building, you can see that the walls of the building has vertical solar panels around the wall. So we want to see how this building performs. So that's facing south, east and west, and north does not have any because of how the solar rays falls on the building. So one of the interesting observation with this building is that we can see that we generate good amount of power in spring and fall compared to other buildings which generate more power in summer time. So with having vertical walls, you can actually have an even curve than your peaks that you get in the peak solar times. So what is involved in the technology that we are using? So we can go to any solar site and we can install something called the e-gauges and cities to monitor power. We not only monitor power for generated by the solar, but we also monitoring the weather condition, like what was the illumination, what was the wind speed, is there any shadow? And the reason we are doing is we are trying to compare between a simulation versus what's happening in the real world. Does the simulations give correct results when you are installing solar? One example I'll give is a lot of people install solar and wants to have the right capacity, but sometimes they install solar panel where there could be a shadow in a particular season and you are not getting the full capacity. So that's something we are looking into. Then also we are looking into, based on the data, failure of solar panels, which is very interesting because when your solar panel fails, a small array can fail and you can slowly lose power even without knowing. And the way they detect that is to fly drones on top of the solar panel, and where there is no generation, you get a hotspot. So what we are doing, we are building an algorithm based on artificial intelligence because we have all the failure data. So we can see which panel fails and we get notified immediately like this panel has failed, so you can take some action. So here is some comparison that you can see that I was talking about. Here you can see that the solar generation for the building on the left, which is the vertical solar panel, versus our rooftop, which is horizon, like rooftop solar panels, how the energy compare. So here you can see that we have more generation during earlier months when we are entering summer, and here we have more generation when we are entering the month of April to around September. So late fall and winter, this vertical building is doing well versus the rooftop. You can see the rooftop is kind of declining and this has good power. So that's an interesting one. So you can combine a vertical and a horizontal one to get a more steady power source. So these are some of the areas we are looking into. One of the interesting thing here, I'll show you what happened during the solar eclipse that happened. So you can see the solar panels are very sensitive. So this is the irradiance curve that you can see. I think that's the green line, and then the blue line is the power generated. So they are highly correlated, and this is the time when the solar eclipse happens. So you can see the small dip in power. So it's sensitive. The reason I put this graph is because if you have a very environment where there is a lot of smoke and pollution, then solar panel might not perform optimally. There could be a little bit of dip in power. So during smoky days that can happen. So in your simulation, if you are installing solar panel in an area where there are a lot of pollution, so you have to take care of this because there is a dip like that and we can see that. So that's a fun graph. So now we talked a little bit about generation. So there are other forms of generation we are also trying in our campus, like geothermal generation of heat from waste energy, and all of this. So that will be our integrated energy source plan. Now we'll talk a little bit about how we are reducing the energy demand in our campus. So the problem statement is we can save 40% of our energy in our building operation by doing a few things, which is very lucrative when it comes to a financial standpoint. So in Canada, some of the institutional buildings range from 1.5 to 2.5 gigajoules per square meter. So that's your building energy intensity of building. Healthcare facilities are more because they need to run their HVAC more often in a different way to make the environment safe. And most of this energy comes from the HVAC system. So one of the strategy involved is to reduce energy by optimizing the use of HVAC system. So what happens is most of your HVAC systems are designed back in time and they run at the full operational speed of the fan all the time. So in a cold country like Canada, you bring in air from outside, which is at minus 20, let's say, and you warm that air up to heat your building. So this happens even if no one is inside the building and the HVAC is running full time. So what we have done as a pilot study, we have changed how this HVAC operates by installing air quality sensor inside the building and also some outside the building. So if you monitor the air quality inside the building, what you can do is you can, based on how many people are in the building and your air quality, you can control the HVAC system. For example, if there is a forest fire outside your building, then you can make a decision like we'll run the HVAC system internally instead of bringing in air. So that you can make that decision. If there are more people, then you increase the speed at which your HVAC operates. So one important thing that to consider, your fan speed is actually proportional to the cube. Your power is proportional to the cube of fan speed. So if you reduce your fan speed by half, then you get 8 times the power savings. So that's what we are doing, and we are estimating a power saving of 70% in this particular building. And if we scale this across the campus, then we can have tremendous amount of savings. So here, as you can see, that's how our HVAC is running. That's the top blue line, and that's our peak demand. And today, we can go on a time-based cycle, or we can go on a demand-based cycle, which will save a lot of energy. So our estimated energy savings for this building is 10.5 metric tons of CO2 per year, just by doing this simple, putting these simple IoT devices and having that algorithm to control HVAC system. So last but not the least, so here are some of the impacts we have created during doing some of the projects. So we trained our students, we partnered with our industry, we get valuable insight, we do knowledge dissemination among all our partners and the community. And these are some of my team members who do all the good work, and I am presenting their work over here. And thank you all for attending, and I would like to thank all our partners and funders in this journey. Thank you and have a good day.
Whoops, sorry. Yep. Okay, good. Here it's good. Okay. Sorry for the small 20-minute delay. That wasn't in the plans. So nice to meet you, everyone. We have a small crowd here, but it's okay. I'm going to explain for you two what we do. So at Cap Solar, we power the future of solar mobility, and we're going to explain how we're developing solar power mobility. So I'm going to start with a small story. I personally am a mechanical engineer, and I started around 10 years ago my studies. Initially, when I started, I was a big fan of automobile, of cars, of big engines, and but then when I got into engineering, I realized that this technology is just too old. It's not clean, it makes a lot of noise, it's too archaic. So I was like, how can I make better with mobility? And then I discovered electric vehicles. I was like, oh, maybe electric vehicles is the future of mobility, where how can we make it better as a mechanical engineer? That's what I was starting to think about. And then I met my father and I introduced electric cars. And my father is the latest possible adopter of technologies. He got a smartphone 2 years ago. I'm not even joking. He was using a Nokia for the last almost 20 years. And I pitched electric cars. And what he told me kind of made sense. He brought up range anxiety, he brought up infrastructure issues, and I was like, okay, he's right, and that's a problem. So how can we solve these issues? If you can, we don't have time, but let's do only one quiz question. Get your phone, scan the QR code on the screen, and answer the question appearing on your phone. Oh, wait, try now. Okay. Are you seeing the questions? Is it working? Good? Okay. Start answering now. So the first question, if all vehicles in Europe became electric, how much additional energy would we need to power all these fleet of vehicles? Just so that you know, today we're producing around 2,400 terawatt hours of energy per year in Europe. So give me your answers. Okay, I see 250, 500, 1,000. 250 is getting in the lead, almost 1,000. Oh, there's a war. The right answer is 500. So today we will need to add an additional 500 terawatt hours of energy in the grid in order to power all the vehicles if they were electric. Now, next question. What actually? Yeah. So we will need to power 580 terawatt hours per year, which represents more than Germany's current electrical output per year. And just so that you have a fun fact, it represents 26,000 round trips from the sun to the earth in an electric car. Next question. How many additional public chargers would we need to power this electric vehicle fleet? Today we have only 600,000 vehicles. Try to answer the questions if you can. Okay, 5 million, 10 million, 10 million in the lead. More. The right answer is more than 20 million. We will need 22 million additional chargers compared to today's only 600K chargers. This represents almost 400 billion euros of investments and a 3,800% growth in charger infrastructure. So when I pitched the idea to my dad, I started thinking, what about solar energy? Could solar energy actually help in this problem? And yeah, we call this vehicle integrated photovoltaics. So solar energy, solar panels integrated in vehicles. Last quiz, and then I leave you alone. So you scan the code, put in your name, and then you answer the questions. So the first question is, how much electricity could Europe save thanks to solar panels integrated in cars? Okay, 150. 150 in the lead. 200. 150. Okay. The actual answer is 150. Good, people. The next question. How many charger installations could we avoid thanks to solar energy in vehicles? You have 5 seconds. Okay, 1, 2, 5. 5 million in the lead. We could save more than 5 million charger installations in Europe thanks to solar energy. Pratham, you're the leader. Thank you very much. So we could save 170 terawatt hours of energy per year thanks to solar, which represents probably around 50 billion euros, and we could save more than 6 million 6 million chargers thanks to solar energy. So if it works so well, why aren't all cars equipped with solar panels? That's the answer I'm going to give you. So first, everyone thinks that solar energy is costly and inefficient. That was the case until 2023. So in 2023, solar energy became the cheapest source of energy since the era of dinosaurs. So it's not costly. That's wrong. It's a wrong fact. And it's efficient. We're today almost at 30% efficiency for cars. Second, custom integration. That's actually a big problem. So you can see here on the right, on the left actually, Sono Motors. It's a well-known German company developing solar panels for vehicles. And they had big issue in integrating solar panels on cars. Every shape, every surface, everything is different. So how can you make this scalable? Finally, aesthetics. That's just plain ugly. You can't put solar panels like these on Mercedes. No one will ever accept. So how can you make solar panels sexy? That's the main issue. So now how to do correctly VIPV? You see that on top? That's a Mercedes with solar panels. You don't see the solar panels. So they did a good job, but it was super expensive. So now the first thing is you need to have realistic ambitions. You need to be able to say, okay, solar panels can be interesting for vehicles, but how can it be? Second, aesthetic solutions. You need to build aesthetically pleasing solutions to the eye because people like cars for what they look like. And third, you need to be able to do custom manufacturing. Universal designs just don't work for cars, integrated solar panels. Thanks to all of that, you can have a big environmental impact. So when you design solar cars, you need to take into account, okay, I could potentially get carbon credits out of this project. Now, what can solar do and can't do? First, realistic ambitions. With a car, on average in Europe, you could get around 20, 30, 40 kilometers per day, which roughly represents 30% of the average daily commute of people here. And you can also have a huge grid impact. As I mentioned, you could have $40 billion less of investments in infrastructure. Second, how can you have aesthetic solar panels? There needs to be a big focus on collaboration. So you can develop the sexiest technology if you want, but if Mercedes-Benz wants to grade it, it serves no purpose. And after that, you need to invest in this kind of technologies. Today, solar energy is all about cost, not aesthetics, efficiency as well. And finally, standardization limits VIPV. Thank you very much. Standardization limits VIPV's potential because we only want to make one specific size solar panel. You need to be able to say, okay, I want to make custom. I want to make different sizes, shapes, colors, whatever. And you need to be able to develop this at scale. So how can you do customization at scale? And finally, we need governments that support this kind of concept. So you need to be able to say, okay, solar panels on cars make sense, it saves carbon emissions, so let's get incentives on board. And the result is a strong environmental impact. So you can get almost 30 megatons per year of CO2 emissions avoided, and that's not even taking into account battery savings. You can get 30% less lifetime energy consumption, and you can get a 10 to 30% extension in battery life on your vehicles. That's not even taking into account everything else in transportation, only cars. If you take trucks, marine, recreational, low-speed vehicles, all of these, you would get a huge impact with solar energy. So to conclude, solar energy is really the way to pay really pay forward the electric mobility and sustainable mobility segment. So it reduces grid independence. It requires aesthetic development, though, and scalable solutions, but everything results in major environmental benefits and also more adoption from people. Thank you very much. You can contact me at this email address if you want. You can go on our website, understand a bit what we do. And yeah, we had a Q&A, but this guy here will kill me, so if you have any questions anyway, you can tell me after the conference, or you can ask them right now if you want. Thank you very much. Okay, I did it quick.
Thanks very much. Yeah. Oh, thank you, Manny. I just sipped it, so. Okay. Right. Okay. Getting started here in just a moment. So far, I just have my fellow presenters, so we'll see if any friendly fire, they call that, right? That's right, yeah. They'll hear my voice. It'll be so compelling. People just choose to sit down. Am I too loud, or am I? Like, hey, you, sit down. Get out of there. Take a look, yeah. I know they want us to get started in a moment. I think they're recording or streaming, so we'll give folks just another minute or two. Too close or too far away? It's not loud enough. You should tell them, because they've got gain controls and stuff in there, so. Prospect coming? Yeah, I don't know.
It's okay. Actually,
Yeah.
just wait for like 5 minutes. That's
Yeah.
I'll give you kind of like a.
Okay. No. Yeah. Are they ready in the back? They're ready for us to get started. Manny, you can hear okay? All right, great. Well, thanks everybody for joining us. We're going to talk a little bit about batteryless sensing today. So the topic here, no batteries, no limits. Talking about this concept of self-powered IoT. So the previous session, we were talking about solar for cars. We're going to talk about much smaller scale self-power here. So the Internet of Things has a scale problem. If you take a look at this chart here, you can see back in 2012, the IBM Watson team, they thought there'd be 1 trillion IoT connected devices just 3 years later in 2015. 2015 came and went, and each successive prediction has been much, much smaller. So this trillion node IoT, it's not that people don't want the data. They absolutely want the kind of data you'd get from 1 trillion nodes of IoT. But there's something limiting our progress in this way. If you look at 2017, the next team at Cisco that took a swag at this, it didn't go down by half to 500 billion. It went down to 50 billion, fractional. And then the next swag someone took at it, 25 billion. Today, in 2025, we actually have somewhere around 20 billion IoT connected devices in the world. And that includes everything, a smartwatch, your toaster, your washing machine. Industrial IoT is a very, very small fragment of the IoT devices that are out there in the world. And yet, there's incredible value that should come from this for manufacturers. AI models, MI models, they need data, continuous data. But we're not where we should be. So here at ShopLogix, we think we have a couple good reasons why that explain what's going on. We'll back those up with some data from the industry as well. So when you add a battery to a piece of equipment in your facility, you've now made a commitment to go back and visit and replace that battery, even if the asset that you're monitoring is in good condition, right? So that's going to require a trip on its own. And on top of that, it's going to require personnel. I've been in and out of hundreds of industrial facilities. I've never met anyone with the title battery changer, right? That job doesn't exist, but it would have to support a trillion node IoT environment. So we're taking maintenance personnel, people with a great deal of expertise, pulling them off their regular jobs to now go replace batteries. They should be focusing on the specialized tasks that they've been trained to do, not running around changing batteries. So this introduces a whole new set of perpetual maintenance tasks. And then finally, these sensors are often, the batteries for them are often made out of, oh, you're right, sorry about that. You're one slide behind. These batteries are often made out of heavy metals that aren't easily recycled, and then they package them to keep them intrinsically safe. A lot of the batteries inside IoT sensors and industrial IoT sensors end up in landfills. So that's really unfortunate for the environment, but it also introduces risk when you're using batteries at scale. here's some photos in June of 2021. This was the scene in Morris, Illinois, where a warehouse that was storing industrial batteries caught fire and burned for days. The local fire department used a specialized industrial fire suppressant called Purple K that they used to put out industrial fires. They said, the fire chief said, this fire laughed at that. So to put out this battery fire, they had to bring in truckloads of dry Portland cement and smother it. It didn't burn like a regular fire did. And the smoke was toxic. So a huge environmental catastrophe just based off of storing batteries. Now, why was this such a severe fire? Most industrial batteries are made out of lithium. And lithium burns hotter. Lithium fires burn hotter than a typical fire. Not only do they burn hotter, they can't be put out with water. Water actually is a source of ignition for lithium. So if you store lithium batteries somewhere where they can get wet, they're much more likely to combust. So pretty terrible potential environmental implications of having more batteries out there in the world. But when you put them into a facility to use them, there are going to be trade-offs as well. So since you're committing to the perpetual maintenance, you're going to instrument fewer assets. The sensors themselves make trade-offs. They ration the amount of data they send to milk the life of that battery as long as they can. So you end up using the minimum amount of data to lengthen out that battery life. AI and ML models perform poorly when they're starved for good data. So if you make this compromise and say we're going to use a battery-powered sensor, and by the power level of the sensor, it dictates you're going to report a couple times an hour to a couple times a day, it'll take you much, much longer to get sophisticated AI or ML. And that's something we've seen in talking to data scientists. The more good data you can feed one of these systems, the faster and more effective they'll be themselves. So reason 2, why have we fallen short? These layers of typical IoT solutions, the asset, the sensing modalities you need, the connectivity and backhaul, and then the analytics layer in the cloud, each one of those represents sophisticated and complex environments that have to be dealt with on a case-by-case basis. If you want to gain insight into a specialized piece of industrial equipment, you have to go and figure out how to mount it, and then figure out what to do with the data when it comes out the other side. But we're not the only ones who thinks this is a problem. One of the sponsors of this show, Bain, did a study specifically on why industrial IoT predictive maintenance has stalled back in 2019. They boiled it down to 4 points. 1, the IT teams aren't prepared for this kind of scale. If you talk to the IT teams around a plant, it's their job to keep humans connected to the internet with their phones or laptops, small amounts of data per person. If you start treating every industrial asset in your plant with the same connectivity needs, the IT departments are not resourced for that. The fictional trillion node IoT, we'd have to have IT departments far greater than they are today if we were going to hand it off to them. Secondly, if you put this in the hand of a process engineer, you're asking them to become an expert in all the things on that previous slide, the protocols, the backhaul, the analysis. If you try to pull something off the shelf that's pre-built to do it, we had a customer that brought in Wi-Fi temperature sensors and then tracked the data that came out of them. Their IT department found that data went to 4 different countries. So you don't know what you're introducing when you bring in off-the-shelf parts to solve these complex problems. There are huge potential security implications. Finally, let's say you get a data point out off of this battery-powered system. Many of these cloud platforms don't have a clear connection to your energy usage or what to do once you've gathered the data. So we offer a different paradigm here at ShopLogix. We're launching 2 new products as a part of this show. They have a couple things in common. For starters, they're always on, continuously sensing and transmitting. They're designed to fit the asset perfectly, and they use harvested energy like heat or light to power themselves. These are ruggedized sensors. It's not a science project. We've been working over 10 years developing this technology. It's already in place at dozens of industrial sites in North America and Europe. So that ATEX or C1D2 certification makes sure it's safe. And finally, maybe the biggest piece, they don't require batteries to operate in perpetuity. Take the data that comes out of those, and now that you've solved the battery problem, instead of getting a couple data points an hour or a couple a day, we can stream continuous insights, what they call hyperscale data. So our sensors report in once a minute. If you're used to going out and spot checking these industrial assets, by hand once a year, in the first hour our sensors are out there, you'd have 60 years worth of data. We also can analyze and monitor that data and then alert you when something needs to be changed. So here's a picture of our smart steam trap monitor. The real definition of how to be batteryless here in the case of something like a sensor, it's a little bit different than our previous presenter who talked about the electric car powered by solar. So instead of having a big battery and getting a huge exposed solar cell to capture it, we know in an industrial environment we're going to have to get by with maybe small amounts of light or heat. We're going to have to catch as catch can. So we started by lowering our power efficiency as low as we could. And that starts with the battery itself. So by pulling the battery out, and making a system that can run off of harvested energy. We've got a perpetual harvesting system where we just run it at neutral, essentially. No loss. We can actually gain a positive charge when we need it. And that's possible because we've got unique technology at the silicon level. It starts with the radio. So we've developed a radio that runs 1,000 times lower than Bluetooth. I'm going to give you a comparative example. Oh, here's one of the steam trap monitors. So if you'd like to see one in action. At the base of this clamp, there's a few wires. I'll pass this around so you can take a look. That's the thermoelectric generator. So there's two pieces of dissimilar metal there with a transfer agent. If one side is warmer than the other, then it'll start to generate electricity. I'll just pass this around. Feel free to take a look. So in that sensor, the biggest consumer of energy is the radio, right? I'll give you a reference point. I'm wearing an Apple Watch. This is like the most power efficient consumer electronics device on the planet. It runs all day, and the battery is about the size of my thumbnail. The big consumers of electricity on this watch in order are LTE, Wi-Fi, the screen, and Bluetooth, right? So 3 out of the top 4 are radios. That's a very power-hungry thing traditionally in electrical communications. Our biggest power consumer is also the radio, but the radio we've developed runs 1,000 times lower than Bluetooth. So that's what allows us to use a small harvester like that. If I wanted to power my Apple Watch off of a solar cell, it'd have to be like the size of this table and directly under a bright light. So by lowering the power floor from a consumption level, we can get away with a really humble harvester like that. And it's easy to find a 1/2 inch of hot bare pipe around a steam system or a playing card size worth a spotlight to power a sensor inside an industrial facility. It'd be much harder if you had to depend on conventional high power electronics and then get a solar cell the size of that table somewhere in the middle of your shop floor. So by the time we finish designing this kind of sci-fi technology and get it out into a plant, we've thought through all the details necessary to make it work for industrial manufacturers. So in addition to the sensor hardware itself, we provide monitoring. We provide a cloud dashboard you can access from any modern web browser. But we have subject matter experts in the loop that can provide analysis. So that way, if you have a question about one of the insights we've derived, you can speak to a real human on the phone and they can explain it to you in context. In the case of the steam trap monitor, we hired a 25-year steam fitter from our local union hall, kidnapped him, and he helps us interpret that data. So we're going to take a look at some industrial applications. I'll talk a little bit more about steam systems themselves. The U.S. Department of Energy states that steam traps fail at a 20% clip annually. So if you have a steam system, which many of the manufacturers here at the show do, it's a constant source of waste. When steam traps fail open, you're basically sending steam down the drain. Think of it as keeping the windows open in the winter while you're trying to heat your house. The implications of that measured in dollars are tens of billions of dollars a year globally wasted. But there's also CO2 implications. To fire that boiler, you're using natural gas, or in the case of some of our customers, coal. And so the carbon impact of wasted steam is pretty severe on the environment. If steam traps fail closed, you have a risk of interrupting your process. When water goes places it's not supposed to in a steam system, that's a hazardous condition. That can cause explosions, expansions, it can damage equipment, and stop you from making. So that's why steam traps are important and top of mind to manufacturers. Here's an example of one of our customers in Ohio. The steam trap's actually here on the right-hand side of the screen. But this trap clogged and water backed up, and that Y strainer there was the softest metal in the chain. That frozen condensate expanded, busted through, and they were purging 120-pound steam to atmosphere. Not perfect on my metric conversion. What's that, like 10 bar or something, right? Somewhere in that range. So this is a hazard. It's dangerous, but it also can affect your process and introduce downtime. So if you think about the old way of staying on top of your steam traps, a modern manufacturing site could have hundreds to maybe thousands. To get up out of a chair and spot check each one each year is very labor intensive. So people aren't doing it very often. But the conventional way of monitoring a steam trap is to take an ultrasound gun or a thermal camera and go spot check each trap. You're only getting a minute or two worth of data out of the entire year. It's a pretty small sample size. The battery-powered sensors that have been tried to solve this problem are expensive. You're going to go back and visit the trap to change out the battery now. And as a result, we're just not seeing people adopt them at scale. So here's a photo of an actual steam trap with the sensor applied. I passed one around. If folks have entered in late, come see me after the presentation and we can show you kind of what our harvesters and sensors look like. But we clamp a sensor onto that hot pipe, just a 1/2 inch of bare pipe, and the heat that emanates off of it is enough to power the sensor perpetually. So you don't need to penetrate the pipe. You don't need to touch the steam itself. Just having a warm pipe you could feel hot with your hand is enough. And then it'll take a continuous temperature measurement. We also run a flexible probe to the outlet side. So this is kind of like a coat hanger. You form it once with your hands and it stays put. And then you clamp that probe to the outlet side. And now you have essentially a thermal powered temperature sensor. As long as there's heat flowing through that pipe, it'll keep the sensor powered and report continuously back to the cloud. Here's our machine health monitor. These are actually two on an electric motor with a pump. So on the left-hand side there, we're using a photovoltaic harvester. On the right-hand side, we're using a thermoelectric generator. This is a hot water feed pump. So we know if the pump's running, it's going to be warm. So we can use that small-scale thermoelectric generator there, and that's enough to keep that sensor alive. On the other side, the electric motor doesn't always generate a lot of heat, but it's in an area where there's light. So you can use either one of those harvesters. I have a couple of those thermoelectric generators here. I can pass them around if you want to take a look. Inside there is that same CBEC device I talked about earlier. So two pieces of dissimilar metal with a transfer agent. And if one side's warmer than the other, it's like 15 degrees F or 8 degrees C. That's the temperature differential you need. That's enough to generate the electricity we need to power these sensors in perpetuity. A close-up view here. Those are magnetic. So you can epoxy them down if you have a machine that's not magnetic, or you can just place that thermoelectric generator on there. In addition to harvesting energy to power the sensor perpetually, it can also take a temperature measurement. So that's an additional data point that you can trend to understand the behavior of your asset that you're monitoring. These typically go on electric motors anywhere from 1/8 horsepower to 1,000 horsepower, and at multiple points along the machine train. So what we're doing with this triaxial vibration device is taking 3 measurements in the same location where someone would walk around and take 3 measurements by hand with a single access handheld accelerometer before. And we're doing it once a minute. So you get this tidal wave of data compared to the old way of doing things. But we can also use PV. And so once again, blown up for detail here, but this solar cell is about the size of a playing card. And we can go, actually with a larger form factor PV, we can go all the way down to 66 lux, but this small playing card size, 200 lux, that's enough to keep us powered perpetually, and that's less light than we have in this room right now. So what does that mean for manufacturers? Right out of the box, they're going to have a complete solution from cradle to grave that'll take care of them without having to go through difficult integration. Our IoT gateways speak to the cloud natively using LTE, so you don't have to factor in your own IT department or bring your own backhaul. You're not adding this new maintenance task of replacing a battery every couple of years. And in addition to that, you're going to get continuous 24/7 monitoring and alarming without having to go and spot check yourself. We'll diagram of how the data flows. So from sensor to gateway, we use that proprietary low power radio protocol I talked about, the one that runs 1,000 times lower than Bluetooth. Oh, this is exciting. I think we may check around the corner. If you can hear me in the control room, I've lost my slides, but I can see now. Oh, there we go. Very good. Thank you. Oh, now we're back on the desktop. There, very nicely done. From the gateway layer up to the cloud, it looks like a very standard IT transaction. So the uniqueness of being batteryless, that's all handled here on the edge. In the harvesting and the sensor hardware, the gateway speaks that proprietary protocol. Once you leave there, it looks like any of the other IoT measurements you're taking. What makes us special is down there at the physical layer. From there on up, you just get continuous hyperscale data that we can feed to any number of systems. We offer an AWS-based cloud platform that provides analysis and visualization, but we also have a full stack API where we can send that data anywhere. So when you start thinking about your own facility, you can send those notifications anywhere that you want them. Our stack includes a REST API, so you can pull specific data, or webhooks, so you can set up your systems to listen for changes in status of an asset. A common integration our customers love is SAP, so now you've got a perpetually powered self-running sensor giving you data once a minute. If there's a change in an asset's state, it'll trigger a work order right away. And then you know to roll the truck and take care of the problem. On the other side, if you just want to take that hyperscale data and send it somewhere else, like put it into your data lake, we can do that as well by streaming data over standard protocols like OPC UA or MQTT. Finally, we can just send you an email, an SMS, or a notification through the API if there's a failure, so you can always stay in touch that way as well. We adhere to strict security protocols through our company. ShopLogic has been around for 20 years, doing business with some of the world's biggest manufacturers. So that ISO certification or the SOC 2 certification for data security, make sure you know that everywhere along the chain, from the encrypted data that goes between sensor and gateway, all the way up into the cloud platform, your data is going to be safe. So let's talk about some real-world applications and tie that back to the savings that are possible here. This is a medium-sized inverted bucket steam trap with one of our monitors on it. If you were to walk through an industrial facility, this would be about the size of a roll of paper towel. Hold it in your hands. You can see that the lines that run through it are 1 inch in diameter, but it's actually not the line size that determines how much waste there is. Inside, there's a series of reducers, and that's how we get to that orifice diameter. So this is a low-pressure steam system for heating and cooling. It's running at 9 psi, which is below 1 bar, right? Okay, I'm doing my bar math. Reasonable cost of steam. This trap, if it's filled, is $14,000 a year in wasted steam. On the vibration analysis side in our cloud platform, taking a look at the continuous data that comes out, these are minute-to-minute readings, and we visualized here the frequency magnitude pairs for the vibration that come off the sensor. So in the case of this one, low-level vibration, structural looseness. That means the motor is probably not down all the way, tightened down all the way, or there could be something like soft footing. But you can see all the way up into things like early stage bearing wear on the right-hand side of the screen when we get to 60,000 cycles per minute versus the low-level vibration. With just a glance, once a minute, you're getting all the data you need to figure out how that asset's performing. All right, so here's another steam trap. This is a smaller one. It would fit in the size of your hand. Higher pressure, though. And as a result, you can see just a small steam trap, something you'd walk past every day, could be $24,000 a year in waste steam. How do we deliver value to our customers with continuous sensing? Well, if the old way of doing things is to wait, up to a year between inspection and repair, and we know that this trap is a liability of $24,000 a year, this is a real example from one of our customers in the United States. They put our sensor on. 2 months into their annual inspection cycle, the trap failed. They knew down to the minute because they had continuous sensing. If they had waited to act based off the old inspection method they were using, we can confidently say that trap would have sat there for 10 months blowing steam, and they would have lost about $20,000 of steam down the drain. So the beauty of having all this metadata about the application itself and then the minute-to-minute data of how the asset's behaving, you can be very intellectually honest in calculating your savings, and they're defensible. There's no greenwashing in solutions like this when you have that much data. So let's take a look at the carbon impact. So for a plant that had, let's say 500 steam traps, kind of a medium-sized steam system, just by finding those same failed steam traps with no new net labor, just changing the traps you would have changed later anyways, but finding them sooner because of continuous sensing, you can reduce about 3,350 tons of CO2 due to not overproducing steam at the boiler level. If you take the equivalencies of these, that's like pulling 600 plus passenger cars off the street, or this is my favorite stat, the 115,000 incandescent bulbs. When you walk around one of these industrial plants, somebody probably got to the bulbs 2 decades ago. There are very few opportunities remaining in industrial environments to get these kinds of savings realized with such little net change in labor. So that's what I think is it's pretty remarkable about continuous monitoring of steam systems. Okay, so those are some real world examples. You saw the solutions here. Please come visit our booth. We can show the software in real time. We have the hardware out to play with, kind of all the pieces of the solution there. I think we have a moment for questions if there are any burning questions, but you can also find me once I get off the stage. So thanks so much.
Oh. Is it off? Oh. Good. Yeah. Can you hear me? Yes. Okay. I'll get started. All right. Thank you, everyone, for joining. My name is Sujin Ren. I'm the Green Hydrogen Lead at Hatch. Today, my presentation is on thermal considerations for pressurized hydrogen storage at industrial scale. So today, I'll give an overview. Is my mic cutting out? Okay. Give an overview of who Hatch is. I want to share some of the projects that we're working on in hydrogen. I'll give some examples of storage that we've designed on projects. I'm going to go through the thermal analysis, and really focused on what happens when you rapidly discharge hydrogen from storage tanks. Share kind of how we implemented solutions regarding the thermal results on real projects, and then some takeaways. So just a bit about our company. So Hatch is an engineering and advisory and project delivery service provider. We have 65 offices around the world. Here in Germany, we have an office in Essen. We are currently involved in about $75 billion worth of active projects in over 150 countries with about 10,000 employees and over 6 decades of experience. We started out in Canada, which is why we're part of the Canadian pavilion. And one of our big differentiators and something we're proud of is that we're 100% employee owned. Hatch works across kind of 3 main segments: energy, metals, and infrastructure. And we look at hydrogen across all 3 of those sectors. And this is just some of the projects we're involved in, and I'll share some more as I go through the presentation. So one of the very first kind of flagship projects in green hydrogen for us was with Raglan Mine. This was an energy storage demonstration project in northern Quebec. It involved a small electrolyzer, hydrogen storage, and then a fuel cell. So the 3 tanks in the top left there are the hydrogen storage tanks. They store about 300 kilograms of hydrogen. We did that project. We were involved right from conceptual design through to execution and construction and commissioning support. The next one on the top right is the Bécancour facility with Air Liquide in Quebec as well. They installed 20 megawatts of electrolyzers in 2021. And Hatch's role in that project was we supported some of the engineering as well as the project management and construction management for that. In the bottom left is a hydrogen injection skid that we supplied to ThyssenKrupp to run some hydrogen injection trials into a blast furnace. And then the bottom right is with the Belledune Port Authority in Atlantic Canada, looking at exporting various hydrogen derivatives to Europe. So specifically on kind of like the large industrial scale electrolytic hydrogen projects, we generally find that a lot of our projects fall into kind of like 3 main use cases for hydrogen. So, the first is around using hydrogen as a feedstock for chemical conversion, be it green ammonia production, e-methanol production, to make sustainable aviation fuel, or to make liquid organic hydrogen carriers. And a lot of those are for, a lot of the projects we're involved in involve exporting that product either to Europe or to Asia. The next kind of category that we find a lot of our large-scale projects to fall under are using hydrogen as a reducing agent, and that would be to make hot briquetted iron, which is a precursor to green steel. And then the third bucket is using hydrogen as a fuel source, so either blended with natural gas or 100% fired into turbines and burners for power generation or to use as process heat. So in all of these cases, hydrogen is being considered or implemented for many of these projects. And often it's gaseous hydrogen storage that's being considered because the derivative process does not require liquefaction, and often they're co-located. So it lends itself to looking at gaseous hydrogen storage. So I'm going to talk for the next couple slides. I've kind of grouped a lot of our projects into 2 buckets, and I'm going to talk about that in the next couple slides. So the first one is around using hydrogen storage in these export projects that we're working on. So making green ammonia to ship to Germany or to Europe, or looking at making HBI, in South America to ship as well. And then I'm going to talk a little bit about some of the implementation trials that we executed and are under construction now. So in terms of hydrogen storage that we are seeing in export projects, so here's 3 examples of projects that we are involved in. These are front-end engineering projects. A lot of these are very large scale, talking about the couple hundred megawatts to a gigawatt range. The first one is a green ammonia project in Canada. This is with the North Atlantic Refinery. They're contemplating about 240 megawatts of hydrogen with 170 kilotons per annum of ammonia production. This project is looking at around 2.5 tons of storage, which equates to about 30 minutes. And that's really to accommodate a slower response time for the derivative process, which is the ammonia synthesis process. The one in the middle, to make methanol, we're looking at a project in South America. Slightly smaller capacity than the one in Canada, but it's actually looking at a slightly larger storage, 3 tons, which is about 1 hour, and we're looking at that to provide storage due to power intermittency from connecting to the grid there. The last one is to make hot briquetted iron, HBI, another project we're working on in South America. Fairly large scale, 900 megawatts to make 2.1 metric tons per annum of HBI, million tons per annum. For that one, we're looking at about 1.5 tons of storage, which is about 5 minutes, and that's really just to safely shut down the DRR plant. So I guess where I'm going with this is all of these projects are looking at, in the tons range of hydrogen storage, but it's to accommodate fairly short durations of buffer capacity, and that's really because there's intermittency in the process. Then I want to get into where we are also seeing the use of hydrogen storage. So we're also involved in a couple implementation trials, so actually like using hydrogen in an application, seeing how that application responds to hydrogen, and often those projects are looking at hydrogen storage as a means to trial without the need to build a lot of production infrastructure. So 2 projects that we're across, the first one is with Rio Tinto. It's in Australia. This is a brownfield demonstration, and what they are testing is that hydrogen is going to be used as a substitute fuel for their calcination process. For this project, they're looking at 4 tons of on-site hydrogen storage in order to conduct their trials. So a little bit more on this project. So there is a fairly small on-site electrolyzer that will generate hydrogen, and then over several days, it's going to get compressed to over 200 bar. It's going to get stored in type 1 tanks, which are just carbon steel all metal construction. And they're storing about the 4 tons, and then they're going to let it down to about 10 bar and deliver it to the calcination process. So Hatch was involved in this project right from conception to execution. We were the full engineering service provider for the compression, storage, and delivery system. And the project is now under construction, so it's a pretty exciting to see something real in hydrogen. And I just wanted to give a visual of this is what 4 tons of pressurized gaseous hydrogen looks like. So there's 5 banks of tubes there, and I've just thrown up kind of a representative image of what that looks like. The next project I want to touch on is in Canada. Sorry, my mic keeps cutting in and out. The next project I want to touch on is in Canada. This is with Atura Power. This is at their Halton Hills generating station. And another brownfield project that they are looking to blend and co-fire hydrogen with natural gas into CTGs between 5 and 15% hydrogen by volume. And for this project, they're looking to deliver 2.5 tons of hydrogen, where that hydrogen will sit on site and be used for the trial. So here's an image of their generating station. This is actually one of the CTGs that we're looking at here. So hydrogen will be delivered in tube trailers. Unlike the Rio Tinto project, the hydrogen's going to be in type 4 tanks, which are composite tanks. It's about 2.5 tons of torque, as I mentioned, and for this application, it's going to get let down to 50 bar and then delivered to the existing natural gas fuel lines for both. There's 2 CTGs two CTGs on site, combustion turbine generators, and this site has about 680 megawatts of power production. Similar to the last, we were the engineering service provider for this project. We were involved from concept to detailed engineering execution, and now the project is under construction. So here is a rendering of their facility. It is existing, even though this is a rendering. I think I have a pointer. Oh, maybe I don't. The two big gray boxes are the two combustion turbine trains. There are 4 tube trailers that are shown there, and kind of a representative image of what those tube trailers look like. So that is going to equate to about 2.5 tons of hydrogen storage on site. So next I'm going to go through the thermal analysis that we did for the Atura Power project. So hopefully what you gathered from the, so hopefully what you gathered from some of the previous slides is that these are fairly large scale projects in terms of these are existing facilities that are looking to use a large amount of hydrogen, and because of that you need large flow rates in order to trial the hydrogen into those existing facilities. And so when I mean large flow rates, we're talking over 1 ton per hour is required to conduct a lot of these trials. To fill storage, I think the thermal, or the understanding of the thermal considerations are more well understood. You see that a lot with refueling stations where they have to pre-cool the gas, or with compressors, there's interstage cooling. So really the focus today I want to talk about is some of the depressurization effects, which either are less known to a lot of our clients or sometimes overlooked, especially with these front-end engineering stages where you don't maybe go into the detail, but it is something that I think we should be considering at an earlier stage in a project. So for this, we did do a computational thermal analysis where we looked at large flow rates discharging from storage, and ultimately these results were used to inform our project design and execution. And I'm just showing here kind of examples of the 2 different types of tanks that I've just talked about. The focus really was on the first tank, but we also did some analysis on the second, the type 1 tank there, just to see what the results would compare with. So in terms of our methodology, we looked at both a 1D and a CFD model. We took geometry directly from the tank OEMs to simulate, real-world scenarios in terms of geometry. We also looked at the model validation in terms of feedback from tank OEMs as well as literature review. I'm going to share 3 cases that we analyzed. The first one is looking at one blending of 5%, which is the minimum flow rate we were looking at, into one of the combustion turbines in a winter month in Canada. The next is 2 combustion turbines at 15% blend in winter, and then the third is 2 CTGs, 15% blend in the summer. For this analysis, we didn't consider crosswind effects, so potentially these will be a bit more conservative than what you would find in reality. So the next, I'm going to present or discuss the results in a couple graphs in the next couple slides. So the first one, are the results of the 1 combustion turbine blend at 5% in winter, in Canadian winter. So we're talking like -15 is a starting temperature for the gas and for the tank. So I'm showing here the temperature profile of the outer shell of the tank, the inner shell of the tank, and the gas temperature. So I think the big takeaway here is that you see significant cooling of the gas and tank. I think a lot of people think with hydrogen, maybe the reverse Joule-Thomson effect, it's going to go up, but it actually significantly drops, and that's from the pressure volume work of the gas expanding out of the tank. Here you see actually the gas temperature drops by more than 30 degrees. So it's something that needs to be really considered, especially when you're rapidly depleting these storage tanks. So the next is looking at a larger flow rate, also in the winter month. This one has even a more drastic decrease in temperature. And what we did find ultimately from this analysis is that the gas cooled below the limits of some of our downstream components that were existing in the facility. So a lot of components that you get with hydrogen, they kind of generally come in 3 bands. There's the minus 20 degrees components, minus 40 degrees, or then you go into cryogenic service and you're at the kind of minus 173. So unfortunately, we had some components that were rated to minus 40, some that were rated only to 20. But in both cases, you'll see here that it actually dropped below both of those limits. The next is the summer, and in this case, slightly better results because we're starting at a higher temperature. And luckily for the immediate components downstream, which were rated to minus 40, we actually had no concerns in that summer case. So just to summarize, we are predicting that you will see significant cooling of the gas in tank if you were to rapidly deplete from storage. This was actually corroborated with the tank OEMs that have done some trials in the US, slightly warmer weather, but they've seen similar kind of gas cooling, icing up around their tanks, which I think is an agreement with what we found here. Some of the components in the downstream system were not acceptable, and I'll talk through how we dealt with that. The summer conditions were a little bit better. So if you're in a warmer climate and you're dealing with this rapid depressurization, you may not have as big of an issue to deal with. And then a bit of a bonus result here is that we also compared to a type 1 tank, and type 1 tanks actually had improved performance, meaning they didn't drop as much in temperature, and that's due to the materials of construction of the type 1 tank versus the type 4. Type 4 is much more insulative. So in terms of some project solutions, what did these results inform in terms of the project itself? So we ended up having to select certain downstream components for low temperature, making sure that those limits, the minus 40, we could try to achieve where possible. It also allowed us to validate where we were going to put some of the thermocouples for monitoring of the system during operation. Ultimately, we had to implement some operational constraints due to material temperature limitations. So in those winter cases, they dropped below the minus 40, so we ultimately needed to put in some operational constraints in the winter time, meaning we couldn't blend as much and we couldn't deplete the storage as rapidly. We did at one point look at evaluating the need and the design requirements for gas preheating. Ultimately, our client, Atura, decided to go with implementing those operational constraints instead. But alternatively, we could have included a gas preheating system so that you wouldn't have those operational constraints. And then finally, our client looked at how does those low temperatures impact the gas that's being combined with the hydrogen gas that's being combined with the natural gas, and how does that impact the overall performance of the power plant. So just in terms of some key takeaways, so hopefully you got from this is that depressurization from hydrogen tanks at industrial scale is one of many engineering challenges to manage on these types of projects. Many hydrogen projects remain first of a kind, and it makes us having to go back to our basics and really understand the fundamentals of what's happening and make sure those are properly integrated into the design. We see that a lot in various aspects of a hydrogen project, be it optimization of what is the right sizing of the project to more kind of technical challenges like the one shown here. And then finally, successful hydrogen projects necessitates strong engineering partners. A little pitch for Hatch, so come find us, come talk to us. We're at stand E62. Thank you.
Good afternoon, ladies and gentlemen. Sehr geehrte Damen und Herren. Welcome to our panel here. My name is Gert Stupp. I'm the director of the Office of Research at the University of Alberta in Edmonton, Alberta, Canada, and we're very happy to be here. Our talk today, and I'll just give you a little bit of background before we start introducing our panelists here, is complementary international perspectives on a practical hydrogen transitions, aka a hydrogen-based economy is attractive, but how can we make it happen, right? And so with me here today are our three esteemed panelists, Dr. Amina Robinson-Fayek, the Vice President of the University of Alberta, and Amina, if you wouldn't mind just giving us a brief context of the relationship of the U of A with the hydrogen economy and so on.
Thank you. Thank you everyone for attending this session, and thank you Goetz for the introduction. So the University of Alberta is a top 50 university internationally, and we're also in the top 10 for energy related subjects. We have over 140 researchers, 1,000 students and postdoctoral fellows working across campus in many energy related topics. We're very interdisciplinary in our approach. So this covers 10 faculties, and we also have 12 industry-focused research centers working in different areas related to energy. In 2016, the federal government awarded us $75 million to launch the Future Energy Systems program. This is a program that has helped us really look at how we transform the energy sector, looking at existing energy systems and what's required in the future. To date, we've funded over 150 research projects through this initiative. What's really exciting is we're building on this capability, and through industry demand, we launched what's called the Canadian Net Zero Energy Solutions Initiative. This is a program that involves 5 complementary areas, and it involves multiple disciplines across campus. So we're focused on hydrogen, carbon capture, utilization, and storage, resilient grids and critical minerals, storage, and also land and water reclamation, which in our province in Alberta is quite important for not only dealing with legacy energy systems, but also reclaiming some valuable minerals. We've raised over $113 million to support this initiative, and this is a combination of industry funding, government and provincial funding, as well as community involvement. What's really exciting is we recently launched a new center. It's called the Center for Hydrogen Innovation, Workforce Development and Outreach. So not only is this center focused on developing the technologies needed to address our energy challenges with a focus on hydrogen, but it's also very much a hub that brings together a number of industry partners, organizations across Alberta, and is very also focused on the training of the next generation of energy leaders and ensuring that we do the appropriate outreach to ensure that hydrogen is not only developed but also accepted. We also have a strong focus on northern and indigenous communities and ensuring that hydrogen is accessible and affordable across these different groups.
Thank you very much. So the next person I'd like to introduce is Brent Lakeman. He's the Executive Director of the Edmonton Hydrogen Hub. And Brent, if you could explain a little bit what the hub is and how that ties into.
Sure, yeah, good afternoon. The Edmonton Region Hydrogen Hub, we were actually Canada's first hydrogen hub to be created 4 years ago now. So we've been at this for a while, and the reason we were set up back then was really recognizing in Canada we produce about 3 million tons of hydrogen per year. Within Canada, about 2.5 million of that comes from the province of Alberta, and within Alberta, about 2/3 of that number comes from the Edmonton region. So we've been producing hydrogen and increasingly lower carbon hydrogen for quite a long time now. Companies like Shell Quest, they've been using carbon capture and storage with the natural gas steam methane reforming process for hydrogen production, again, for about 10 years. And now we're the home to some even larger projects looking at net zero hydrogen production, again, from natural gas with carbon capture and storage. So we like to say producing hydrogen is not really the challenge. We can produce extremely large volumes of low carbon hydrogen from our low cost discounted natural gas combined with our excellent geological formations for long-term safe CO2 storage. But now it's really about not just producing it, but using that hydrogen. So what the hub has been about is really about creating the environment to allow us to open up new demand for hydrogen across different sectors. certainly heavy industry. Most of our large projects are really meeting industrial needs like renewable diesel production, now net zero chemicals production with companies like Dow, supported by Linde with their project. But in other applications in the transportation sector, in the heat and power sector, the aviation sector. So the hub has really been about that. So quite a large number of demonstration projects in, I like to say, planes, trains, automobiles, as well as trucks and buses using hydrogen fuel cell technology, as well as hydrogen diesel dual fuel technologies. So really an exciting range of initiatives underway in the region. But the point is not just to do pilot projects, to begin to scale that. Let's start to get the infrastructure in place so we can see more widespread hydrogen adoption.
Thank you very much. The third panelist here is Dr. Stefan Sterleppe of the RWTH Aachen and also the Managing Director of the Clusters for Future and Hydrogen. So could you please provide us a little bit of context of what your connection is there?
Thank you, Gertz, for the nice introduction. Good afternoon, and thank you for joining our discussion today. Yes, I'm wearing two hats today. So I'm a member of the RWTH Aachen University, one of the largest technical universities in Germany, but also in Europe, with 45,000 students, more than 500 professors, which is actually not a lot for this amount of students. And we are focused on a lot of technical topics, and we have a very long, even decades of hydrogen research. And then in 2019, we figured that when people come over to us, when industry partners come over and ask, okay, what hydrogen expertise do you have in production or storage or utilization? No one had the overview of all of that. And so we founded in 2020 our Center for Sustainable Hydrogen Technologies, and then we aligned all of these members, and we have way over 50 professors now involved, all aligned on the full hydrogen economy. And this brought us to apply for the Clusters for Future initiative here in Germany, which is one of the major initiatives from the Federal Ministry of Education and Research, which is open for any topic. So a lot of medical topics, also AI topics. And we applied with the topic of hydrogen successfully. And so we are funded with 45 million over 9 years. And we includes RWTH Aachen University as the lead actor, but also Research Center Jülich as our partner, and also in the first funding phase, 45 industry partners, and now quite a few more industry partners as we just started our second funding phase, and we cover the full value chain. So we have projects on hydrogen generation, mainly focused on electrolysis. Then we have projects focusing on storage, mainly focused on high pressure storage and carbon fiber tanks. Then we have the distribution part and pipelines, the electrochemical compression also, and separation from challenging mixtures, and then all kinds of use. So we have a strong focus, a strong emphasis on mobile applications like fuel cells, but also hydrogen engines, but also on industrial applications like steel industry, like glass industry, and everything you might imagine. And then the most important part actually is that we try to connect all of these. We go very deep into the technical details, but then we come up again on the overall system level, and then we want to connect, and we find that all of these actors face actually the same challenges, and that's, I think, what we want to discuss today.
Thank you very much. That's very fascinating, because there is two things that become very clear. It's a very broad field, and there is a field with lots of needs, right? And you started off by saying that your cluster started off from a direct industry need, that there is a vast field, but not much clarity what the path forward is. So are there any needs in that sector that you can speak to maybe that might help companies to approach that?
Definitely. So I think one of the first needs is actually overview. So there are so many hydrogen activities and so many funding schemes and so many opportunities, but there are not this many companies earning money today with renewable hydrogen at least. And so we need to start with the overview. Everyone needs to find his or her own business model, but it's all connected. So you need to know all of the different parts. You need, if you are focused, let's say, on fuel cells, You need to know the car which you, or the truck which you mount your fuel cell on. You need to know the storage system. You need to know the gas station, the refueling station, and you need to know that it actually takes not only one electrolyzer, but also 3 stages for compression to get the required pressure level for that. And I think there we need a lot of overview, and then we need innovation. So we have a lot of technologies available, but the technology is at 90% development. So it's all prepared. People have it in their books. You can purchase prototypes, but it's mainly prototypes. But hardly anyone has experience, let's say, with 1.5 million kilometers of hydrogen truck operation. And that's what we need to find. And there is still so much room for innovation in there.
Thank you. So if I may ask Brent Lakeman the next question. So we just heard that it's a vast field with a lot of technical challenges. And so say for the companies who have identified they want to get active in that space, what would barriers be in that to make that step beyond that technical point of view?
Sure. Well, and I think maybe people that have been in the hydrogen space are aware we have many technologies to produce it, but you do need to have that offtake. Who are the clients, the partners for that hydrogen? So again, fortunately, in our part of Canada, we have a very robust industrial ecosystem, starting from our petrochemical companies, our refineries, and so on. So we have that very strong industrial offtake. So that's really allowed us to then move to the next level of decarbonization of these facilities through hydrogen. Again, from some of the technologies that work at scale, again, that we have experience with in Canada. SMR, and now moving to autothermal reforming. So I think that the biggest barrier is to who is your partner, who's your customer. So industry is the easy one, though. I think we've talked about transportation, and then it starts to get a little more difficult. So how do we start to build out that infrastructure that's needed for the demonstration of these vehicles? And our hub has been spending a lot of time on that. How do we partner in the mechanisms to get new refueling stations in place when one pilot project, that might not be enough to really justify what infrastructure needs to be in place. So how do we all work together? So one thing we did a couple of years ago was launch something we called the 5,000 Hydrogen Vehicle Challenge, which is a way to really show we're all working together to scale hydrogen vehicle adoption. But it means we have to work very collaboratively, the producers of the fuel, with the OEMs and the vehicles, with the training organizations like the universities and the polytechnics. Even groups like insurance has to be part of this conversation. So we're really trying to put a bit of a rope around all these different players that need to be part of it, because one group just can't do it alone. And that's just transportation. It gets even more challenging probably when we get into things like hydrogen for heat and power systems. Some of our companies are very interested in that, but that also requires some policy shifts. Right now, how in Canada, or at least in Alberta, how is hydrogen treated in the utility framework? So that can be a big barrier if we don't have the appropriate regulations and legislation in place. So I think it really depends if you're looking at the industrial applications, the transportation applications, or other sectors, and then even aviation will have its whole other set of requirements. But it is really about working together in a more collaborative manner to build out these new markets in particular.
So when we have, let's say we're a company that has a plan of making that transition, the next step then is, how do we build a business model around this? So what would the implications be for a company to make that step and then sort of take it to the next step forward?
Yeah, no, that's a really good question. And I think we are looking at new business models. So I think in many cases, there's a need for innovation in that space. So how can the company understand, what's the mechanism that allows its technology to be scaled for more widespread adoption, again, on vehicles? Is it the purchase model, leasing models? So I think there's a strong interest in opening up the door to new types of models. And I don't think, I certainly don't have the answers to what is the right model, but I think that's where, we need to see more integration of different approaches from the researchers, the technology developers, to the business community, groups that maybe have experience in other sectors that have seen new markets being established. And I think maybe just coming back a bit to Canada, we've got a strong ecosystem for supporting some of the innovations that are required. We have Alberta Innovates in our province. We have federal entities as well. And I think there's really an expectation, if companies are coming forward, they have thought a bit about the business models. How will they scale their technologies? Because we've seen so many, challenges getting through the technology valley of death that we do need to take new approaches now.
If I can come back to you, Stefan Strelepa. So is that a question that comes up with your companies as well? And is there any support they can access to make that from both the scientific or from the economic side that you can facilitate, or how does that work?
Yes, sure. So I mentioned we just started to our second funding phase, and during the transition from phase 1 to phase 2, we asked ourselves exactly that: what can we provide to our members, but also to new partners, how they could benefit, and how could they provide their piece of puzzle to the hydrogen economy. And I think people always talk about offtake, because offtake might be the most important part. We need to have the offtake, then we will have the hydrogen production. But if you now take the offtake side, the offtake view, then you need to have affordable hydrogen. And our approach is to focus on decentral systems, so to build up small local communities where you produce your own hydrogen, store it some way, maybe transport it, maybe not, and then use it again. And then you have a closed business model where you have secured offtake and secured hydrogen supply. And that's our approach.
Thank you very much. So I would like to come back to you, Amina, because that is a very important point. We heard a lot about the industrial side of that and the needs, but it became very clear that innovation and the connection to research is core to that. So can you describe a little bit how your institution positions itself to respond to the current and the future energy needs in that space, like looking ahead? That's where the university is good at. So what does that look like for the University of Alberta?
Thank you. And I want to just touch on some of the comments that my fellow panelists made. So, you know, Aachen is one of our key partners. In fact, we're heading over there now, and we follow a very similar model. And our areas of focus, when you talked about the integration, I think that's critical. You cannot focus on any one aspect. You have to look at the entire life cycle and the value chain. I think the scale-up piece is what you're referring to, and I think, Brent, you referred to the scale-up. The biggest challenge we have is that we are disconnected. You know, universities working on a lot of very innovative technologies, you know, low to mid TRL. We've got industry, wonderful uptake in terms of some of the more advanced technologies. What we need to do is de-risk the middle piece. And in order to do that, we need to co-locate ourselves with some significant investment on pretty large scale facilities that allow us to actually work side by side. So the biggest thing I see that we're trying to do is we're creating the centers that are very industry funded and industry focused. Government, of course, is a key player in that. And I mentioned our hydrogen center, but we have the Center for Energy and Mineral Processing, many different centers. But we're still missing that big funding gap to allow us to de-risk those, take them from pilot and lab scale to truly full scale. And we can't do that alone. We all have to do it through a continuum of working together. So I still think there's a tremendous opportunity for Canada and internationally for us to do that. I think the other thing I want to mention is when I talked about our research, it's not hydrogen alone. It's hydrogen, it's CCUS, it's grids, it's storage. We cannot solve our energy problem without looking at how these technologies are related. And so in the case of Alberta, we're producing a lot of hydrogen with natural gas. We still need carbon capture, utilization, storage. We're looking at green hydrogen, but we have to look at the greenhouse gas emissions over the entire life cycle, because in order to produce, you know, a wind farm, we're also using techniques that are potentially producing greenhouse gas emissions. So we really have to look at the entire value chain. And I think universities working with industry are very well positioned to do that. We also need government at the table to provide some of the very significant de-risking funding that's required. And we need to look at doing things differently than we've done them to date if we're really going to solve this problem. We also have to look at energy affordability and reliability. So meeting our greenhouse gas emissions is important, but how do we ensure our remote climates, our northern climates, are achieving, you know, these technologies are feasible in those contexts?
Thank you. Can I ask, so now that you work in this field, there's all this research going on, you're closely working with industry, how does the institution then mobilize that technology and that intellectual property that is developed into industry? How does that mobilization work?
So we're actually co-developing it with industry. In fact, our centers are, we have scientific and management advisory committees where industry is working with us hand in hand to define the problem and co-develop the solution. And I think, you know, many of my colleagues are here who actually work in these disciplines have been very successful in developing practical real-world solutions. Where I think we need to get to, though, is some of these solutions are implemented immediately. We're very good at bringing together competitors and developing things not only for individual companies, but for the industry at large. I think we still struggle with, we can test things up to a certain point, which is, you know, maybe even a little bit beyond lab scale to pilot scale, but to get them to that truly commercial stage. And, you know, I think we talked about the variation of companies. Some are small, they don't have the risk tolerance or capacity of larger companies. Some are large. You know, this is where really partnering together in a model that isn't disjointed and having that large scale funding. When I, you know, as I visit Europe, I see some countries doing that very, very well. They have the large scale infrastructure that allows industry to come and test the technologies that are being developed by the researchers and get them to that full-scale market readiness level. So I think we're doing a lot of that, but I think there's still sort of a limit to what we can do with industry without some of that major, large-scale, mission-driven funding that is being talked about, and we just need to see it come to fruition.
Thank you. If I can come back to you, Stefan, in this case. I'm very curious to learn a little bit more how then this collaboration between industry and academia works. Is there ways, a mechanism to leverage industry funding into larger scale problems that, or projects, and how would that work?
Yeah, well, in Germany we are quite lucky that we have quite a good funding scheme. So we have quite a few public funded or public funding calls where you can apply for, and we use that a lot for joint projects together with industry. And then we build the project together. The industry comes with the requirements, and we come with our innovative ideas. And so it's an iterative process, and then we need to align on the product. And I think there are plenty of examples how we do that. One example we achieved lately is to build up a demonstrator, which is maybe on the pilot level, but a Ford passenger car with a hydrogen combustion engine. And it's a very innovative one because we combine the stoichiometric and the lean operation. So let's call it a diesel-like and gasoline-like operation. And we combine the advantages of both with no CO2 emissions. And that was only possible because we had quite strong industry partners. And now we build on that, even though Ford needed to retire its German research activities. We have found a new partner, Deutz, and now we are going more into the heavy-duty applications and continue. And now we want to demonstrate not only that it's working, but also that it's working at zero tailpipe emissions. And then we demonstrated it's working, and then the companies can use that to go to their customers, for example, big logistic fleet companies. And that's exactly what they want to see. And I think we need to use our countries, Germany as well as Canada, as a showcase for our own products, so that we can say, okay, here, that's how it's working, and there you can jump on.
Speaking of jumping on, I might just jump on that one because I think it's an excellent example, very similar, I think, to what you're talking about, but it's because one of our local Edmonton companies, and probably 4 years ago, nobody would have even heard about this company in the hydrogen space, but they're working on a hydrogen diesel dual fuel combustion system, and they've been able to get incredible traction in a very short amount of time, and partially because I think there's a recognition, let's not let perfection be the enemy of the good. Maybe not a total net zero vehicle, but it really starts to get us on this pathway towards more hydrogen utilization. And it's really because of one of the professors I know at the University of Alberta that had strong roots in Germany, that he was able to sort of work with this company and say, hey, there's a way we can really show this is going to be an incredible bridging technology and maybe just a long-term technology on its own. The company is called DTI, Diesel Tech Industries, but it's been a great example, and now their vehicles are being, municipal fleets are converting buses and some of their trucks. Airports are converting some of their airfield equipment, like the snowplows that go up and down the fields. And other trucking companies are also looking at that technology. So again, 3 or 4 years ago, nobody would have heard of this, but through some of the collaborations with our partners in Germany, with the university, it's really allowed some game-changing technologies from an actual Edmonton company. We're still waiting for fuel cell vehicles, but those always seem to be a few more years behind. But in the meantime, we've got some very lower cost solutions ready to go.
I mean, if I may come back to you. Now, Brent made an interesting point about this international connection. Can you give us an indication how that international collaboration would work from a university perspective? How can we set up these collaborations across the ocean and across different countries?
Yeah, very good question. And I'm really pleased that you gave that example of the dual-use engine, because that's a perfect example of being able to scale up. But it took years, and it took dedicated investment from companies with, in collaboration with our amazing researcher. So I'm glad you asked about internationalization. I think Canada signing on to Horizon Europe is a big step forward. And the reason for that is we've had these collaborations. We have trusted partners in Germany and UK and France and Singapore and India and Mexico. But we've often done it sort of a one-to-one relationship. We try with the funding we have to develop seed grants. We try and get researchers moving back and forth, faculty members, students. Now, with Horizon Europe and other European funding, we have a mechanism for larger scale collaboration. And, we're learning about Horizon Europe. In fact, every time we come to Europe, we go visit our partners who have a lot more experience in that, because these are bringing together the true international consortia. And in Pillar 2, of course, we're now looking at bringing in industry in addition to academia. It's large scale, it's complex. If we're going to solve any of these challenges, we cannot do it regionally or even nationally. We have to test them in different contexts, and our contexts are quite different. So I think the international piece is now becoming much more robust. Of course, we've been doing it for decades, but having a true mechanism is actually bringing us together. It also means that Canada is now at the table, shaping the next set of priorities. And I know we're talking here about energy and hydrogen, but that applies in the health space, it applies in pandemic preparedness, it applies in AI, it applies across many different sectors. So I think this is really exciting. We're starting to see even more focus with our geopolitical considerations. I know in an earlier discussion we talked about research security. It's becoming very robust for us as countries. It actually allows for freer and better research collaboration. And so I think internationalization is taking on an even larger focus more recently. But, in terms of a research institution, having a mechanism is going to make that collaboration broader and more effective. We're developing a Horizon Europe and European Europe strategy, but we also have researchers who are participating in these calls, and so we're learning also through their experience.
Brent Lakeman, if I may come back to you. So now that we have that international dimension, I would like to bring it back a little bit more on a regional and then even a local connection there. How can regions really look into facilitating this hydrogen and technologies and associated technologies, and then also bring it back to the local economies?
Yeah, I think regions have a huge role to play in the hydrogen economy, because we know the challenge with hydrogen is moving it around. You can produce it, you can use it kind of locally within your industries, those clusters, but now we're trying to stretch that boundary a little bit. So Edmonton, or I should say the Edmonton Region Hydrogen Hub, is 14 municipalities that have really come together around trying to pursue this opportunity, not just to produce it, but to use it internally. Now, we also would like to be exporting hydrogen in the form of ammonia initially, and that's requires some high degree of coordination, across regions, across Western Canada in particular. So it's probably two separate conversations I'll get into. Is one, we need this pursue the larger export opportunity. We'd love to export to Europe. There's a few more challenges in moving our product out to the east rather than just going straight west. But nevertheless, I think that's an important market that we serve, the Asian markets. But I think to allow that to occur, we need to build up the domestic use case as well. And that's another reason for the hydrogen hubs. So if we can grow this demand, but we need to also think about, what's that infrastructure that's required to move hydrogen around the domestic economy, and that's where innovation, of course, will play a huge role, because I think that's still probably our biggest challenge is how do we reduce that cost? We can produce hydrogen at a very low cost in Edmonton region, less than $2 per kilogram, but when we start to have to use hydrogen at the pump, it's closer to $20, even $30 per kilogram, so a significant cost associated with transporting it. So we know there's some innovation taking place. There's some companies here from Alberta, Ayrton, for example, that has an innovative LOHC technology. And I think more innovation there is critical if we're going to open up these new markets in heavy-duty transportation and some of those regional movements. I think there's some really interesting things potentially with companies that are in the pipeline space, that can convert those natural gas pipelines into hydrogen use pipelines to allow us to accelerate that activity to move hydrogen around the regional ecosystem and then also around the continental and international ecosystem. But again, this is where I think we need innovation in business models, innovation in the technologies themselves, and how do we connect hubs? So one of our initiatives we've created in Western Canada is the Western Canadian Hydrogen Corridors Initiative to work with other hydrogen hubs like Calgary. So that's our busiest corridor, Edmonton to Calgary, because it's not just going to happen from one end of the corridor. It has to be jointly on both sides, and then other corridors across Western Canada going all the way out to the West Coast. So those regions, those regional-based approaches will be critical, but we also know that each region is going to be a little different. Edmonton is a highly integrated, I should say maybe diversified industrial base. Calgary just launched a hydrogen hub. That will be really helpful for us, but they don't necessarily have that same industrial ecosystem that Edmonton does. So we need to understand they'll all be at different starting points, bring different benefits, different attributes to the table, and again, hopefully we can build off each other's work.
Thank you. So everything indicates it's a very coordinated effort. It's also a staged effort, not just on the technology level, but also in how things get moved around. So I'm wondering, Stefan, if I can come back to you, what incentives exist to implement this sort of an international hydrogen economy, and what could that or what does that look like right now?
Yeah, well, for the hydrogen, for the international hydrogen economy, we have the challenge of transport, and to transport hydrogen as itself is very costly, and well, it's really hard to have a ship transporting gaseous or liquid hydrogen, and I think it's not the most straightforward way. So if we want to have long-distance transport, we need to have pipelines. If we want to transport hydrogen by ships, then we will need to convert it into ammonia or methanol or maybe even DME or so. So there are plenty of derivatives which we could use. And incentives. I think right now our major challenge is that fossil energy is so cheap. And there needs to be a certain CO2 burden for fossil energy carriers. But this will only apply for certain communities. And if we want to have a global and an international transition, we need to have business models where renewable hydrogen is cheaper than fossil hydrogen, where green is cheaper than gray hydrogen. And that sounds weird, but in the electricity world, it's just turning around. So green electricity is becoming the cheapest electricity by now. And that should be the target for hydrogen. And I think which is, at least on the German side, actually I don't know how it is in Canada, but in Germany we say, okay, battery electric vehicles are always good, no matter about the source of the electricity. But for fuel cell electric vehicles, you need to prove that it's green hydrogen. And there's a gap in between, and that's not to be reasoned. And I think that's the main incentives which we need. We need to have very pragmatic approaches, and we in Germany are good to define very safe, very process-oriented approaches, but we always tend to lots of bureaucracy. And there I think we can learn from you to focus more on pragmatic approaches.
And if I could come back to you, Amina, on that very topic. So it's about also That means if we take this a pragmatic approach and recognize this, we can't rely on a single technology, but it has to be complementary adjacent technology that we have to consider. So how does the academic environment help with that? How can they help integrate all this together in a cohesive plan?
Great question. And I wish we were less bureaucratic. I'm not sure we can take full credit for that. But so it's really important that like you say, we don't look at these technologies separately. And the benefits of one often benefit the other. Obviously, in a university setting, we have top researchers working in all these disciplines, many of which work in multiple disciplines. Our centers and institutes bring these researchers together. But we also know that, if we're working on hydrogen, we need the CCUS. So we have our experts right next door to each other. So it's a natural evolution. We also have, our grids and storage. We're not separated from the environmental engineers and the scientists and the chemists. So we naturally have that ecosystem. The other thing that is very important, I think Stefan mentioned it, is the interdisciplinary nature of solving these problems. So often the barrier, although it's technology, we focus a lot on that. It's the social implications of that, the policy, the economics. These things have to be feasible, for different groups with different affordability levels. I talked about our particular challenges in the north and our indigenous and remote communities. Well, batteries don't work very well in the north, so there's a different angle to the technologies that we need to develop. We have communities that are hard to reach, and that's why the dual-use engines and looking at, SMRs and different technologies are really critical to that. We take that and put it in a different context. It might be different, but there's similar challenges we face. So I think our obviously universities naturally lend themselves to that. So that's I think quite valuable. The other thing is we have to look at public acceptance. We saw that in the pandemic, that was often the barrier, and it's no different for energy solutions, whether it's hydrogen, whether it's nuclear, whether it's wind or solar. There's a lot of issues we need to overcome in ensuring that these technologies are integrated in the community and serve that community. So I think we're fortunate because we have all of these top experts in one place, and I can speak for my colleagues. We have a very collaborative approach to how we solve research, not only collaborating with external groups, but collaborating amongst ourselves. And we, with this hydrogen center, I see some of my colleagues, it is not just coming out of engineering or science or business or social science and humanities. It's 60 researchers across campus to date, and it's growing. And so I think we have the right environment and the right ecosystem to do that.
I would like to close this panel with one last sort of crystal ballish question. If we talk about community, if we talk about industry, if we talk about collaboration and making this transition, we need also reliability. And that means we have to think about what are reliable sources for hydrogen. I'm just curious if you have any sort of feelings or thoughts about what that reliable source might look like now, might look like in 10 years, or sort of going forward. Maybe Brent Lakeman, if I can just pass the mic over to you.
Maybe I'll just chime in, and part of this is this past week I was on a tour between Canadian hydrogen hubs and Germany hydrogen hubs, and then they're very different shapes and sizes to hubs, as I mentioned earlier. Some are kind of at a university environment, others are much kind of a larger ecosystem initiative like what's happening in Edmonton. But I'll keep coming back. We're doing this because of climate change considerations. I think there's that urgency of continuing to scale as quickly as possible. So, I'm happy to see some of the large-scale initiatives in places like Edmonton continuing to move ahead. We've seen some struggles, I think, over the past year around hydrogen with different technologies globally, and maybe the cost hasn't come down quickly enough. They're not ready for prime time quite yet. But I think there are some technologies that are moving ahead more, at a scale. So again, we've got some of those examples taking place in Edmonton. So I think it allows that platform to begin to build and maybe bolt on other technologies, other use applications on top of that. So, I'm optimistic that at least in some of these, industrial clusters that are really driving things forward in hydrogen, we are going to continue to move ahead, and we can do it maybe in a bit more of a strategic manner and avoid the hype about trying to actually use hydrogen for absolutely everything and really quickly. But where does it make the most sense? What industries are prone? And again, we've got access to some of these large projects, 500,000 ton per year low carbon hydrogen projects in Edmonton. and being able to demonstrate this is the future pathway forward, at least for jurisdictions where we have those types of resources. But it also allows you to maybe add on new technologies that could be linked in, whether it's pyrolysis technologies, electrolyzer technologies, some really exciting university work on catalytic water gasification technologies. So I think we're going to see all of those, but we need to kind of have that strong foundation to build from.
Thank you very much. I thank you to the audience for listening, and thank you for everything you shared.
Okay.
We can probably together.
Oh, nice. Yeah. Okay. That direction, which is actually smart. Ballard, and then you go to the next slide.
Yep.
Okay. Ready? Okay. All right. Hi, everyone. Greta Kutilenko, CEO and founder of Acerta. At Acerta, we provide AI-powered analytics and quality solutions for manufacturers, where we work with manufacturers across over 12 countries, deployed on 300 production lines, helping manufacturers leverage the vast amounts of data that's becoming available from production, including fuel cell production, to get in front of quality issues and drive efficiencies during manufacturing.
And I'm Andreas Putz from Ballard Power Systems. I'm the principal data scientist at Ballard Power Systems, and we produce hydrogen fuel cell stacks and modules for bus, small ferries, locomotive, and marine applications. As I said, I'm the principal data scientist there, and my job was to get us into the cloud, get us connected with our data, get us connected with vehicle data, but also with data from our manufacturing floor, specifically acceptance testing. And there I take you to the root of our problem. So Ballard Power System is producing high quality stacks and modules, and to keep up the high quality, we have to do very extensive factory acceptance testing. So currently, in extreme cases, these factory acceptance tests can take up to 8 hours. On average, we take to 3.5 and 4.5 hours. But this is still way too long for an automotive standard factory acceptance test. So not only do we incur a lot of time, we also incur a lot of hydrogen costs because we are running them at realistic conditions at high power points for extended amounts of time. The amount of hydrogen we spend on these tests is in the millions of dollars per year. So we have a test bottleneck. So if we want to scale up production, we would have to build more test stations because our production capability would scale linearly with the amount of fab stations we have. We also have limited factory space, so we can't just build 10 or 20 more factory acceptance test stations. We have to be more prudent and more frugal with the space we have available to us. And the last thing is, these test stations are expensive. They have a lot of channels, between 250 and 1,500 channels per test stations. They're difficult to calibrate, difficult to keep in calibrations. So having a platform which helps us understanding our test stations better was vital for us, as well as optimizing our acceptance test. Yep. So really what we want to do to 2027, we want to scale our production between 400 or 500% to what we currently produce. And that would mean currently we would have to buy at least 4 to 5 more of these factory acceptance test stations with a CapEx expense of about $5 million plus several other $1 million for additional hydrogen. So what we wanted to do, we wanted to learn from the data we already have and build a machine learning model which allows us to build an equivalent of the current test at a fraction of the cost and a fraction of the time. So really mainly we want to reduce the time we take from 3.5 hours to about 30 minutes, and with that reduce time, effort, hydrogen costs, labor costs, and everything associated with running these tests. And also we wanted to avoid capital expenditure for new test stations, is that they cost $1 million per test station. And this is where Acerta comes in with line pulse.
Perfect. So at Acerta, we're specializing in creating AI-powered solutions for manufacturers. So one of the elements we provide is an out-of-the-box machine learning platform called Line Pulse,
where line pulse leverages data from production, everything from process information, so various measurements, current voltage readings in through assembly of the stacks, as well as at the end of the line, so at the factory acceptance test station, where they're generating across those 3 hours of testing lots of information and continuous measurement of how every cell within the stack is performing. So with Line Pulse 1, we've deployed the system to start looking at the trends in production from cell to cell, from stack to stack, to see and find early indications of drift or other anomalies that are being introduced through the process. So you can just imagine, across hundreds of, I think it's about 250 different cells per stack that we're looking at, and about a voltage and a current reading at least for every stack, all across those 3 hours. So it's a huge amounts of data that we're engineering initially a certain characteristic out of it across every step of the test to see if there's drift or variation that's happening between the different stacks that are coming through production. And that gives, initially, as part of the solution, gives early indication that there's variation or change in these tests from stack to stack. That gives early indication that something might be changing in the equipment or with the tester. Part of that process, we've also designed a set of models to target Ballard's core case, which is to reduce the testing time. So the major work that we've done together has been to develop a model where we can monitor the initial ramp and setup portion of the test, which is between the first 15 to 30 minutes, and leverage a model during that time to already make a determination if, for example, this stack was tested for the rest of the 3 hours, would it fail or would it pass? So what we were able to do is within the first 15 minutes, already based on the performance characteristics of the stack, identify what's that likely outcome so that the test could be shortened and didn't have to go through the remainder of that testing time, and that way really address some of the challenges that Ballard was experiencing. As part of this process, we've used approximately 700 to 800 stacks that have been historically tested at Ballard, where data was being collected from each of those to develop and validate the models initially, to determine what's that performance and how can we get it to the point that the Ballard system can actually leverage those models in production to make those determinations. Maybe a little bit about the test stand.
Yes, so we are bombarding Acerta with a lot of data, unlike almost any other manufacturing floor equipment. So our test station, which houses the stack or the module, depending on the size, is producing between 250 and I would say 2,000 signals, depending how many cells you have, at a frequency of at least 10 hertz. So that is a lot to process, and typically manufacturing floor tracking software doesn't know how to handle that. So we've worked with Acerta pretty extensively of how to create features from this time series, how to transport this time series efficiently to an endpoint, and how to build this model from there. The other advantage of working with Acerta and Line Pulse is that you always have access to the model. The model is accessible through pipeline. You can package it however you want. And for example, there is this model packaging tool chain. You can deploy your model in your own Docker container, put it into existing cloud infrastructure, or in this case, actually deploy it on an edge device close to the test station. So in the situation where you're looking at very low latency, so milliseconds and lower, you actually want to have your model physically as close to the test station as possible instead of uploading everything to the cloud. And this is where the model packaging comes in and the model development lifecycle. So you have a lifecycle which allows you to deploy this model onto your edge devices through Internet of Things. And your edge device always runs the latest model you wanted to provision for this product line and for the latest test data. And with this, the edge compute actually runs the model, makes the determination whether the stack passes and fails, and feeds this back to the test station operator. On top of that, we can statistically track when we want to run a full test to continuously validate the model. So statistically, we run a full test every so often to make sure that nothing has drifted. And when we detect that things have drifted, we go back into a retraining calibration round. So Line Pulse allows us to track the life cycle, check the quality of the model continuously, and deploy the model either in line pulse directly or really any way we want to deploy the model.
Yeah, and so from that perspective, we've augmented our line pulse platform to be able to have this dynamic automatic deployment of the models to the edge device right next to the test station to perform this analysis and provide recommendations of final outcome of the test, as well as then the line pulse platform continuously monitors data from every new stack that's uploaded periodically to the system and can then retrain continuously on new data to make sure the models aren't getting stale, and we're continuously ensuring the accuracy and performance levels that we've agreed predeterminedly with Ballard would be required to make this a production-ready solution. So talking about results, so far we've seen fantastic results where we've been able to already reduce the fuel cell testing times by 46%, which is huge implication on the throughput of the production line, as well as just savings as a result of that. So from that perspective, again, why 46%? Because again, we're providing the prediction of pass or fail for every single stack. And then in any stack where we're not certain in terms of the determination within 15 minutes, we can continue running that test for another 30 minutes, let's say, to make the determination, or fully run the test on the stack until completion if that performance of the model is not quite certain on the final outcome. But 46% has been a major improvement, which can lead to about 83% improvement to throughput for Ballard's production lines, which is a huge impact, especially as they're looking to scale production of the fuel cells long term. And from that long-term scaling, that implies about a $6 million savings over the next 3 years across labor costs, across new capital investment, and in general, based on other certain savings from hydrogen that Andreas can talk about in a second. But the savings also does not incorporate potential for new sales that then drive through this throughput increase, which is also huge potential for the company.
Yeah, and for us, the hydrogen cost saving was massive. Like at the beginning of the project, before we crunched all the numbers, I didn't think that was such a problem, but especially last years with the rising cost of hydrogen in North America, saving every bit of hydrogen we can has been proven very, very effective and very, very helpful for us.
Perfect. And so from that perspective, from a Certus point of view, this is a huge accomplishment because now in order to replicate some of these capabilities when it comes to a new hydrogen fuel cell production line, it would take us about 21 days to replicate the solution for a new stack assembly line, which is a huge improvement and acceleration for us, especially thanks to all of the work we've been putting in the last almost 2 years in the collaboration together. It's a major improvement and something that we've now incorporated as part of our application as well. And it's been a very positive experience in terms of actually deploying models that are now making direct determination and autonomously controlling the production rather than just making recommendations. So from that perspective, it's a fully closed loop solution that we're now demonstrated and deploying at Ballard.
Yeah, and for us, it was the first foray in really predictive tools, predictive machine learning-based tools, which replaced a full physical test. So having the confidence that you still deliver the high quality we normally deliver with a shortened time was a dramatic improvement. As said, we are looking forward to rolling these technologies out across our manufacturing floor, but also across our products and during the lifetime of our products.
Perfect. Thank you.
Thank you very much.
actually. Huh.
Yes, we're live now.
Back in June 2019, I made a video about energy storage in hydrogen.
We'll get started here in a second.
Oh, fun. Come to the crib.
I have the numbers wrong.
Huh?
I said 12 people sitting here
It was 20, yeah. Yeah. That's it.
Free Canadian beer. This is going to be the best presentation. You'll want to sit down for this. Anyways, just want to talk about today for anybody who's here about enabling the hydrogen economy through the use of AI and digital twins. So we'll be kicking things off. I'm Peter Warren. I'm located out of the Toronto region of Canada. And Lucas, you are?
Yeah, I'm Lucas. I'm located.
Oh, you're quiet there.
Test? No,
Yeah,
there we are. Yeah, I'm located in Munich in Germany. Therefore, responsible for the hydrogen business in Germany.
Very good. And I want to quote somebody, a very famous person in our company that's also part of the Canadian Pavilion, et cetera, Dr. Diane Gushu, who's the researcher for our AI work here at CGI. CGI is a global energy enabling company, but we also work in the manufacturing industry. We work in healthcare. About 90,000 people around the world. Originally founded in Canada with offices here in Germany. We have 5,000 people here in Germany working on all sorts of systems from coast to coast. And here we're talking about the use of digital twins. The concept we're coming up with here is based on an article that Diane wrote, whereas if you have an electron and you want to optimize the ROI on that electron, what do you do with it? Do I sell it to you now for $1 or €1? Do I store it in a battery and sell it to you tonight for $1.50? Or do I make it into hydrogen because I can make more money doing that? And if I make it into hydrogen, do I compress it into ammonia? Do I make the ammonia and sell it to fertilizer? What do I do with this to maximize the ROI? So we're going to talk about digital twins today, and we're going to start off with a great example from Lucas, helping one of our clients, which is just by here, Quest One.
Yeah, so this is one of our Munich clients. Is it working properly? Yeah, so what we basically did is, so normally if you think of like a hydrogen electrolyzer, you have an IoT gateway, which is just constantly sending the data to some kind of data lake. And what we did is we basically equipped each of the stacks individually with a chip, which is then hosting, for example, different modules. And for example, also about anomaly analysis. So if you're talking about peak and spike models, for example, which is then sending the data to the cloud. And the interesting thing is that this is not happening on the layer of an IT gateway, but either on the layer of each stack individually. And therefore, you can control each stack remotely in a much efficient way. And what we implemented anyways is, on the one hand side, more the 3D model, but on the other side as well, the edge and cloud integration. So the application is kind of like running in the cloud, and you also have all the operational insights, meaning if you click, for example, on a different stack in the 3D model, then you see all the properties there and could say, like, hey, there's something running wrong here. Perfect. And I mean, this is just one example of digital twin. But if you now add multiple digital twins, for example, for the supply chain or also for financial markets to it, then you also are getting something which is more pointing towards what we're doing in Canada, which is pizzing.
We're good. We'll just switch back and forth. So I just want to move into here and building upon it. So as Lucas was saying, we've built a digital twin for optimizing the production of energy. So when you're looking at optimizing an electrolyzer and you're looking at all of the different KPIs and key points, pressures, the water flow, everything else, this digital twin maximizes that at a level for the actual operation of that system. What we then do is use a series of stacking of AIs to look at other components. So when we start to stack other components, we're doing this for a company in Canada. They want to also say, I not only want to optimize what I'm making in hydrogen, I actually want to look at the market. What is going on right now? Am I better to make the hydrogen and keep it and sell it? Should I convert it back to electricity? Should I make it into ammonia? What should I do with it? And they're looking at all of their different functions. They're looking at the operational thing of the water, the filters, and so on, and they're looking at this in a complete ecosystem. So they're not looking at, I only make hydrogen, I can make it back into electricity. I could make it into ammonia, I could make it into fertilizer, I could actually take this hydrogen and store it for 5 years if it makes sense. But they also want to know the pedigree of the energy. So people are no longer wanting to know that I've made hydrogen, they want to know the quality of it. We've got into the whole concept of gray, pink, and blue hydrogen, but this is really looking at a quantifiable measurement of the carbon intensity of that hydrogen that we're making. Why are we doing that? Very much like either a fine wine or a fine whiskey, people will pay you more for a premium whiskey than they will a blend. And so the intention here is if you can prove that through this production system that I've used very green electricity, very clean water, and that my total overhead isn't very much, I can actually give a score on how carbon intensive this batch of hydrogen is going to be. Therefore, somebody will pay me just like a premium wine or a premium whiskey more for that. And this is where it's moving forward. So if you want to sell green steel, you need green energy. And so this is all part of the larger ecosystem. But we're also looking at, well, how do I maybe sell the wastewater? How do I sell the excess heat? So we're looking at this as a complete ecosystem. And as we start to then move into their supply chain, I'm looking even at, how do I optimize these things because I might have contractual obligations? What are my regulations requirements? So this digital triplet model actually is stacking up to then a system that then comes back and gives the human factor. I'm just going to put this down for a second. So if you have twin 1 looking at how I'm optimizing system, twin 2 looking at the market, 3 perhaps looking at my supply chain, and 4 looking at other production factors, the digital triplet sits on top and looks at the output of each of these other systems and says, what am I, from a business standpoint, what am I trying to do? What are my key performance indicators as a company to maximize? Maybe it's best to store the hydrogen, maybe it's best to convert it, maybe it's best to sell it back as electricity. What should I do right now to maximize my profits and meet my contractual obligations? So this is when we're looking at these stacks of things, and one of the key factors of this is the human in the middle. We fervently believe that AIs don't make people smarter, but it gives them smarter decision tools to make better decisions. So this is a way of actually empowering people to move through this process. Did you want to add to that about what you've built at this level?
Yeah, so I mean, for us, it was basically first digitizing the physical assets and then adding like a first recommendation to it. For us, this was the peak and spike model, for example, the simple machine learning algorithm, which just looks over a given time and says, okay, I have so many pikes and so many peaks, and this means then, like, for example, hey, given that at each of these particular data points, I, for example, have a rise in the pressure because my membrane was leaking at this particular stack, and then it's pretty easy. Then the 3D model is just colored, for example, in red or orange, depending on the threshold, and then also notification is sent out either via mail, SMS, whatever you want, to the individual operator and to the manufacturer to detect, like, hey, something is not wrong. You might want to have a look over there, over some logs, over some SPS configurations, and then pointing that back.
Yeah, and so this builds upon things. So one is we're helping optimize the making of the hydrogen. 2 is we're maximizing what should I do and trade it. So 3 then is into the situation, how do I prove to you that I've made a premium wine? How do I prove to you I've made a single malt scotch? In this case, how do I prove to you that I have a low carbon product? So one of the things that CGI does is we're actually the elephant in the room when it comes to energy trading. We trade natural gas, electricity, water at scale. And so if you were to go to electrical provider, to your retailer, your supplier, and say, I want to buy only green electricity, there's no guarantee that the electricity coming out of that light bulb is green, but it's a contractual thing. Somebody made 1,000 units of green, so only 1,000 units can be sold. And there's certificates that are associated with that move through. In this model, what we're doing is we're attaching the certificates to perhaps even a physical shipment. You're sending by rail, you're sending it by a truck. When it gets blended into a pipeline or a storage area, it becomes more of a math thing, what's in there. And here in Germany, people really only want to pay for the premium green hydrogen. In the moving forward economy, as it ships from north to south and east to west in Europe, you've got to be able to track it from an economic standpoint and be able to have those certificates. Hopefully that makes sense. So what we do in here is we actually combine those different AIs up here, and then this system here in the middle actually determines from the supplier what information does the regulator need to see. What was my certificate? What to the people that are shipping my material, what do they need to know? Because they're going to put it on their boat or in their truck. And then finally to the end consumer. But there's actually multiple other nodes we could put in there. When you ship something, it's insured. It's insured for its commercial value. So the insurer wants to know that what you're putting on this boat or on this truck is of a certain grade. If it's a blended, cheap and cheerful wine, they're not going to insure it for the same amount as if it's a premium wine, if it's a fine Bordeaux or Riesling in Germany here. So the intention for this model is to enable the ecosystem. We were actually at a trade show much like this a few years ago, and they were all saying, we know how to make hydrogen, and we know how to consume hydrogen. What we don't know is the stuff in the middle. How do we enable an economy? And this is all designed to enable the economy, and we actually measure this effectively like the scope 3 of ESG input to anybody who wants to pick up that hydrogen. So if you want to make green steel, this process can certify what you have came from a premium source, therefore you're going to make a premium steel, therefore you could sell it for a premium price. Anything to add, Lucas? So where we're working in this ecosystem is CGI is working from end to end. So we're working here with the electrolyzers.
Yeah, I guess that's more my point. So we're like working in the south mainly with the production of electrolyzers, of the manufacturers with different companies, and what we really aimed on is that we can actually connect the product data we got from the operating electrolyzers back to the shop floor so that they can improve, for example, their products, but also got to know to these issues like membrane leaks or something way more earlier than before they even happen. Yeah? And I mean, if we then look for their triplet or adding them, then you're moving from the value chain more to the right. Yeah.
That's right. And then we're working with production. So Iberdrola is a company that we've actually worked with. So they have a very large facility making green hydrogen. So they want to know its pedigree. So they need to manage their entire production floor. So we're working right with the large producers. Wind and solar, we actually help run somewhere in the neighborhood of 12 gigawatts or gigawatts, I'll get the number right here, daily in wind and power services. So we understand wind power. Oh, and I lost my slide. It went back. Oh, no, it disappeared. Don't know why, but it did. But we're working through the entire ecosystem. The other thing we do is we get right out to the pumps. So as people start to fill up, there we go, fill up at the pumps and at the other systems, we actually manage that as well. So if you have a Shell card, a loyalty card, that's us. If you process in Canada, if you're any Canadians here, on a debit card, that's us. So we have the ability not only to help from the production at the manufacturing head to the production of people in the energy market, through the transmission and shipping industry, all the way to the fact that we can actually bill you at a hydrogen pay pump. And that's kind of unique. So Circle K, if you actually use Circle K, that's us. So that's CGI in a nutshell and what we're talking about. If you want to see more, come see us at A44 in Hall 17. We're in another Canadian pavilion. It's a short walk. No, it's not. It's a long walk, but it's on your way out. And we'd be happy to talk to you guys further. Thank you very much for your time.
to